Imagine everything you've ever known, every atom, star, planet, and galaxy compressed into a single infinitesimally small point. Then, in an instant, it all explodes outward. Time begins, space unfolds, and the universe is born. This is the story we've been told, the Big Bang as the ultimate beginning. But is this the whole story? Before the first second ticked by, before energy cooled into matter, before even the laws of physics existed as we understand them, what was there? A quantum vacuum, a collapsing universe, a higher dimensional collision, or something we don't even have the words for yet? Let's dig into some of the most mind-bending ideas in modern cosmology and approach the limits of what science, and maybe even thought itself, can reach. Reconstructing a vanished epoch, what physics can and can't tell us about less than zero. When we talk about the beginning of the universe, we often imagine rolling back the cosmic clock, rewinding the galaxies, the stars, the atoms, all the way down to the very first moment. This picture feels straightforward, like running a film in reverse. In physics, we even have equations that let us do something like that. General relativity, our best theory of gravity and spacetime, allows us to take the current expansion of the universe and calculate backwards. We can shrink the size of the universe, going further and further into the past, getting a clearer picture of what things might have looked like just moments after the Big Bang. But there's a point where this breaks down, a wall we keep hitting. That wall is known as a singularity. To understand what that means, we have to start with what general relativity actually does. It describes how matter and energy curve space and how that curvature affects the motion of objects. According to Einstein's equations, if we plug in the current state of the universe, how it's expanding, what it contains, and how matter is spread out, we can predict what the past looked like. This works surprisingly well. It lets us rewind the universe all the way back to when it was less than a second old. But as we push further back, past a trillionth of a second, past even smaller slices of time, the numbers stop making sense. We reach a point where density and temperature shoot up toward infinity. Space becomes infinitely curved. The equations give outputs that don't describe anything real, just mathematical chaos. That's the singularity. It's a point where our current theories fail. In the case of the Big Bang, the singularity sits at time, or t, equals to zero. It's the barrier to knowing anything about earlier times. In simple terms, we can say that general relativity can't describe the universe at the exact beginning, or before it, because the math breaks down. The theory needs spacetime to be smooth and continuous. But when the density of matter becomes infinite, spacetime stops being smooth. It tears apart in a way. This tells us something deep about the nature of our understanding. It means there's a limit to what we can know by using general relativity on its own. No matter how good our measurements get, no matter how powerful our telescopes become, we can't rewind the cosmic movie past that point, not with this tool. Now you might think, why not use quantum mechanics instead? After all, quantum physics is the other major pillar of modern science. It describes particles, energy, and the behavior of matter on the smallest scales. But quantum physics has its own limitations. Quantum field theory, the version of quantum mechanics that combines particles with fields, is built on a fixed space-time background. It assumes space and time are already there, smooth and well-behaved. That works great in many situations, especially inside particle colliders or atoms. But it falls apart when space-time itself becomes wild and chaotic, like it does at the Big Bang. To really describe the beginning, you'd need a theory that combines both general relativity and quantum mechanics into one single framework, something that can handle extreme density and high energy, but also deal with the warping and breakdown of space and time. That's what people mean when they talk about quantum gravity, a theory that doesn't yet exist in a complete tested form. Until we have that, we're stuck. Our current tools let us get close to the singularity, but not through it. This puts a hard boundary on any talk about t less than zero, aka the time before the Big Bang. In classical physics, time is a line, and we can trace it in both directions. But near the Big Bang, the classical picture of time no longer works. In practical terms, it means we can't say what, if anything, was happening before t equals to 0. Some models try to push the boundary by changing how we view the earliest moments. For example, some versions of cosmology start the clock not at t equals to 0, but at t equals to 10 to the power of negative 43 seconds, what's called the Planck time. This is the smallest meaningful unit of time in physics. Below this threshold, quantum effects and gravity are both so strong that we lose all predictive power. It's not just that we don't have the data, it's that the rules themselves might no longer apply. It's as if the entire concept of time stops being meaningful. From this angle, the past isn't hidden, it's undefined. The tools we use to define time and space don't work in that regime. When density and temperature go beyond certain limits, when energy levels become extreme enough, even the language of physics, mass, distance, time, starts to fall apart. This isn't the only time singularities show up in physics. They also appear inside black holes. If a star collapses past a certain point, general relativity predicts a singularity forms at its center, an infinitely dense point surrounded by a boundary called the event horizon. Inside that region, time and space behave in ways we don't fully understand, and once again, general relativity fails at the singularity. This parallel hints at something deeper. The Big Bang singularity and the singularity inside a black hole may have something in common. They might be two examples of the same fundamental problem, our inability to describe extreme conditions with our current theories. Wherever we push physics to its limits, whether at the heart of a black hole or at the birth of the universe, we run into the same wall. What all this tells us is that while our equations can take us incredibly far, they cannot take us all the way. We can describe the expansion of space, the cooling of the early universe, the formation of particles and atoms, but only from a certain point onward. And that edge matters, because it shapes the kinds of questions we can ask and the kinds of answers we can trust. If someone asks what happened a second before the Big Bang, the most honest answer we can give with our current physics is, we don't know, and maybe we can't know. This shows us how far we've come and where the next breakthroughs need to happen. For now, though, we can only approach the beginning from one side, like looking at the edge of a map and wondering what lies beyond, knowing we can't draw it until we invent a whole new kind of cartography. The end of time's arrow. How entropy behaves in reverse and eternal models. We remember the past, not the future. We grow older, not younger. Heat flows from hot objects to cold ones, but not the other way around. All these patterns follow what scientists call the arrow of time, a direction in which events unfold. At the heart of this idea is a law of physics that has never been broken, the second law of thermodynamics. It says that in any closed system, entropy, the amount of disorder, will tend to increase over time. In most of physics, the basic equations work the same way whether time moves forward or backward. If you watch a video of two billiard balls colliding and then reverse it, the backward motion still looks like something the laws of physics allow. But if you watch a glass fall off a table and shatter, reversing that scene, watching shards fly up and form a perfect glass, feels wrong. That's entropy. It tells us that certain processes have a preferred direction. This one-way flow of entropy gives time its sense of direction. In our universe, as far back as we can trace, entropy has been increasing. The early universe was hot and dense, but it was also surprisingly uniform. That's actually a low entropy condition, even though it might not sound like it. As the universe expanded, matter clumped together into galaxies, stars, and planets. These structures added complexity and, in the long run, more disorder. Eventually, stars will burn out, black holes will evaporate, and the universe will become cold and dark, an end stage called heat death. That would be the maximum entropy state. But if entropy defines the direction of time, what happens if entropy starts decreasing? Could time itself reverse? In certain models of the universe, entropy might actually run in the opposite direction during different phases of cosmic evolution. and that opens up the possibility that the arrow of time, as we know it, could flip. Instead of imagining that everything started with a Big Bang and has been expanding ever since, we can ask what might happen if the universe were to stop expanding and begin shrinking. In standard cosmology, this could happen if gravity eventually overcomes the outward push of expansion. Space would begin to contract, galaxies would draw closer together, and the universe would collapse into a big crunch. In some versions of this idea, as the universe contracts, the entropy might not just continue to rise. Instead, the trend could reverse. As matter gets squeezed back into a smaller and smaller volume, some physicists argue that entropy could begin to decrease. That would mean the direction of time, at least as measured by entropy, would also flip. To observers inside that contracting universe, it would feel like time is still moving forward. But from the outside, it might look like time has begun to run backward. This kind of thinking has led to proposals in which the universe has two symmetric halves. An expanding half with increasing entropy, the one we live in, and a contracting half where entropy increases in the other direction. The two are connected at the point of lowest entropy, which would be the Big Bang. This doesn't mean time literally reverses in the way we experience it, but it means the thermodynamic arrow of time, the one linked to entropy, does. In one such model, developed by Sean Carroll and Jennifer Chen, the idea is that the universe can spontaneously generate patches of low entropy space from a timeless background. These patches then evolve in both time directions, away from the low entropy state. Each side sees itself as having a forward-moving arrow of time, and both consider the low entropy point as the beginning. From their own internal viewpoint, each half of the universe sees time flowing outward from the middle. Another place where this idea shows up is in cyclic cosmologies. In these models, the universe doesn't have a single beginning or end. Instead, it goes through an endless series of expansions and contractions. After each big crunch, there's a new Big Bang. The cycle repeats, possibly forever. In these models, the universe resets itself with each bounce. The challenge is figuring out how entropy behaves through those cycles. If entropy keeps increasing with every cycle, it would eventually reach a maximum, and the cycles would stop being meaningful. But if entropy can somehow reset, maybe through quantum effects or exotic physics, then the arrow of time could also reset. Each new cycle could start fresh, with low entropy and a new direction for time. A more recent and technical version of this idea comes from the Conformal Cyclic cosmology proposed by Roger Penrose. He suggests that the distant future of one universe can be mathematically stretched and reshaped to look like the very beginning of the next. The idea relies on the fact that as the universe becomes cold and empty, all matter decays, and only massless particles, like photons, remain. In such a state, the concept of time becomes meaningless because there are no clocks or changes left to measure. Penrose claims that this timeless state can then connect to a new Big Bang, where time begins again. This idea might sound strange, but it's rooted in real mathematics. And it shows just how much our understanding of time depends on the presence of entropy. Without entropy, there's no direction. Without direction, there's no time as we know it. All these models share one idea in common. The direction of time might not be a fixed universal property. It might emerge only under certain conditions, specifically when entropy can increase. If those conditions change, so might time. This is very different from the everyday way we think about time as something absolute, always ticking forward no matter what. But in the world of cosmology, time is tied to the structure of the universe. And if that structure flips, bends, or repeats, then the flow of time might do the same. Of course, these are still ideas. They aren't yet proven. Some models require certain assumptions, like how gravity behaves at very high energies, or whether space and time themselves can stretch and rebound in just the right way. But they show that entropy isn't a background detail, and so by studying its behavior in unusual situations, we may begin to see time as something more flexible, something that could, under the right conditions, fold back on itself, or even run in reverse. Beyond light and matter, could the universe have emerged from pure geometry? There's a shift happening in how scientists think about the universe's origin. For a long time, theories have focused on energy and matter, particles colliding, fields vibrating, temperatures climbing to extremes. But now, some researchers are asking a different question. What if the universe didn't begin with matter at all? What if it didn't begin with particles or even energy? What if everything we know, space, time, light, and atoms, grew out of something more basic? Something like geometry itself. It sounds strange at first. We think of geometry as something we study in math class, shapes, angles, lines. But in physics, geometry can be much more than that. And some physicists now believe that before there was light, before there were forces, before time itself ticked its first second, there was geometry. Not the smooth kind we see in general relativity, but a deeper quantum form of geometry. This idea comes from a branch of research known as loop quantum gravity, or LQG. It's one of the main efforts to build a theory of quantum gravity, the same goal that string theory is aiming for. But loop quantum gravity takes a very different path. Instead of trying to fit gravity into the same framework as particles and fields, LQG starts from scratch. It doesn't assume that space is a smooth background. It says space is made of tiny building blocks, just like matter is. In this view, space isn't a continuous sheet. It's a web made of tiny loops. These loops are not made of anything material. They are pure geometry. They carry information about how space is shaped, how it bends, how it connects to itself. Imagine a fabric, but instead of threads made of cotton or wool, these threads are made of space itself. The loops can twist and weave, forming networks that give rise to the space around us. These networks are called spin networks. Spin networks don't live in space, they are space. Every point in this network holds information about area, volume, and connection to nearby points. And just like atoms can combine to form molecules, spin networks can evolve and change, creating larger and more complex structures. Over time, this network can grow. As it does, it gives rise to the space we live in. But how does this relate to the Big Bang? In LQG, the Big Bang is a transition point where one kind of geometric state changes into another. In ordinary cosmology, we say the universe began at a singularity, but in loop quantum gravity, the singularity doesn't exist. Instead, space can only shrink so far. There's a limit, because the loops that make up space can't be compressed beyond a certain point. It's like trying to squeeze a sponge. It can only go so far before it pushes back. This leads to the idea of the bounce. Instead of starting from nothing, the universe may have gone through a phase of contraction until it reached a minimum volume. At that point, quantum effects of geometry took over. Space rebounded, and a new phase of expansion began. That expansion is what we now call the Big Bang. But it wasn't the beginning. It was the result of a bounce that came before. This idea is explored more deeply in loop quantum cosmology, a version of LQG that focuses specifically on the entire universe. It takes the spin networks and applies them to a simple, symmetric model of space. When scientists run the equations backward in time, they find that the universe doesn't hit a wall at t equals 0. Instead, the geometry transitions smoothly through a bounce. Time continues, but the direction changes. Before the bounce, there was a contracting universe. After the bounce, we get the expanding universe we live in today. All of this happens without matter playing the central role. In fact, these models show that geometry alone can drive the bounce. The loops of space, the structure of spin networks, the rules that govern how they evolve, all of it can produce a universe that looks like ours, even before you add particles or light. This paints a picture of the universe that is very different from the standard Big Bang idea. Instead of time starting at 0, we have time flowing through a transition in the structure of geometry. What's especially powerful about this idea is that it might be testable. Even though these loops are incredibly small, far beyond anything we can observe directly, they may have left traces in the early universe. The cosmic microwave background, or CMB, for example, carries patterns of light from when the universe was just 380,000 years old. If the universe went through a bounce instead of a bang, that early light might contain clues, tiny deviations, subtle fingerprints of quantum geometry. Some researchers have created detailed simulations of how the early universe would behave in loop quantum cosmology. These models show that certain features, such as the distribution of temperature fluctuations in the microwave background, could reveal whether a bounce happened. Others are studying the formation of primordial gravitational waves, which might carry signatures from before the bounce. These are difficult signals to detect, but new telescopes and observatories may one day be able to find them. The idea that the universe could come from pure geometry challenges how we think about what's fundamental. In standard physics, particles are the smallest pieces of reality. Electrons, quarks, neutrinos, all the matter in the universe is made from them. But in LQG, particles might just be features of the spin network. Like ripples in a pond, particles could emerge from the underlying structure of space. Instead of asking, where did matter come from, we now ask, where did geometry come from? And some researchers believe geometry doesn't need a beginning in the usual sense. It could be that the network of loops and connections simply is. It evolves, it shifts, it transitions, but it doesn't necessarily have to start from nothing. That idea is hard to grasp. Our everyday experience is built on space and time. We live in 3 dimensions, we move forward through time, and we see the world as filled with stuff. But if the universe comes from pure geometry, then all of that is secondary. Space and time aren't the background, they're the result. This is where physics starts to overlap with philosophy. If geometry is the root of everything, then the universe might not be made of stuff at all. It might be made of relationships, how things relate to each other, how positions and angles and curves connect across the network. Matter, in that view, is just the expression of these relationships. Reality is not a thing, but a pattern. Inflation's blind spot. What happened before the universe inflated? Inflation is one of the most successful ideas in modern cosmology. It explains why the universe looks so smooth on large scales, why it appears flat, and why tiny quantum fluctuations grew into galaxies and clusters. It describes a short period of time, right after the Big Bang, when the universe expanded faster than the speed of light, exponentially, doubling in size again and again in a fraction of a second. But for all its successes, inflation leaves out one major detail. It doesn't explain what happened before it started. This missing piece is sometimes called the pre-inflationary epoch. It's a blank space in the standard model of cosmology. We know that inflation must have begun around 10 to the power of negative 36 seconds after the Big Bang. But what set the stage for this enormous expansion? What was the state of the universe before inflation kicked in? The theory of inflation usually starts with a field called the inflaton. This field is not made of particles in the usual sense. It's more like a field spread across space, holding energy. When this field is high up on its potential energy curve, it causes space to stretch rapidly. Eventually, the field rolls down its curve, losing energy and heating up the universe, creating all the matter and radiation we see today. But for this to happen, the inflaton field must have already been in place, sitting in a very specific state. Inflation tells us what happens if we have an inflaton field ready to go. But it doesn't tell us why that field was there in the first place. It doesn't say how it got into position, why it had the right properties, or what created the space it inflated. So between the breakdown of relativity and the beginning of inflation, there's a slice of time we don't understand. What might have filled that gap? One idea is that the inflaton field was not the first field to exist. Some researchers have proposed the existence of earlier fields, sometimes called pre-inflaton fields, that shaped the universe in its earliest moments. These fields could have triggered changes in space, setting up the conditions inflation needed. They may have pushed the inflaton field into the right place, creating the high energy state that allowed inflation to begin. These fields might have had unusual properties. Some could have been unstable, decaying quickly. Others might have carried different types of energy or interacted with space in non-standard ways. In some versions of this idea, these early fields don't cause inflation themselves, but they help prepare the geometry of the universe, smoothing out large irregularities or pushing the universe toward a near-flat shape. Other models suggest that the early universe didn't begin in a smooth, simple state. It may have been full of turbulence or random quantum fluctuations. Over time, these fluctuations might have created small pockets where the right conditions for inflation appeared. In this view, our universe is one of those pockets. Inflation happened here, but not everywhere. Some explore ideas where the early universe was in a quantum state, neither fully classical nor fully defined. In this view, the entire cosmos was described by a wave function. This wave function didn't describe things like temperature or distance, but probabilities and amplitudes. At some point, the wave function collapsed into a classical state, and inflation began. This kind of picture is common in quantum cosmology, where space and time themselves are treated as quantum variables. There are also attempts to build models that stretch smoothly from quantum gravity to inflation. One approach is to embed inflation within loop quantum cosmology. In these models, the universe contracts before expanding. At its smallest size, quantum geometry takes over and replaces the singularity with a bounce. After the bounce, the universe enters an expanding phase, and right after that, inflation begins. The inflaton field is still there, but its behavior is influenced by the quantum geometry of the bounce. In these scenarios, the pre-inflationary universe contains real structure, perhaps a contracting universe, perhaps a mix of fields, perhaps even echoes from a previous cosmic cycle. Some of this structure might survive the transition and leave signals behind. Detecting these signals is difficult, but not impossible. Experiments like the Planck satellite have already mapped the CMB in great detail. Some researchers believe that signs of pre-inflationary physics could be hiding in areas of the sky where the fluctuations are slightly weaker or less random than expected. If the inflaton didn't start in a completely uniform state, or if it had a brief interaction with other fields, that might leave fingerprints in the spectrum of density fluctuations. These small irregularities could be studied in the distribution of galaxies or the polarization of the CMB light. The physics of the pre-inflationary era is happening at energy levels far beyond anything we can recreate in laboratories. That makes it difficult to test theories directly. We have to rely on indirect evidence and be careful not to overinterpret small anomalies. Still, the possibility remains that we could learn something about what came before inflation, not just from deep theory, but from actual observation. If we can figure out what prepared the inflaton field, we might learn what laws or conditions came before the visible cosmos. That could push us closer to answering some of the biggest questions. Why is there something rather than nothing? Why does space behave the way it does? Why does time move forward? Others remain cautious. They point out that inflation works well even without knowing what came before. It may be that the pre-inflationary phase is unknowable in principle, that any signals from that time were erased during the violent expansion. Or it may be that the idea of before inflation is misleading, that time itself didn't have meaning before a certain point. Bubbles in the void, eternal inflation, and the infinite cosmic fracture. As the theory of inflation has developed further, something strange appeared in the equations. In many versions of the model, inflation doesn't just happen once and end. It continues in some parts of space, branching off and creating new regions where inflation ends in slightly different ways. This leads to a much bigger picture, one where our universe is just one pocket in a vast and growing cosmic foam. This idea is called eternal inflation. It means that while inflation ended in our part of space and gave rise to galaxies and stars, it may still be going on elsewhere. In fact, it may never stop. In some areas, space continues to stretch faster than light. And within that ever-growing space, Little bubbles can form where inflation comes to an end. Each bubble becomes its own universe, with its own physical conditions and rules. Fluctuations in the inflaton field might help the field roll down its energy slope, bringing inflation to an end. But in some patches, the field can randomly jump up the slope again, which would keep inflation going longer than expected. The regions where it ends are surrounded by inflating space that is still growing, and in that growing space, more patches appear. Some regions inflate longer, others shorter. Some never stop inflating. As this process continues, the structure of the universe becomes fractal. The bubbles don't collide or mix because the space between them is still inflating. That fast expansion stretches everything apart, pushing the bubbles away from one another faster than any signal can travel. Inside each bubble, inflation ends and the familiar universe begins. But the details of each bubble can be different. The laws of physics might vary slightly or drastically. That's because the vacuum state of the inflaton field can fall into different configurations. In some bubbles, the constants of nature might be similar to ours. In others, they might be wildly different. The masses of particles, the strength of forces, even the number of dimensions, these could all change from one bubble to the next. This idea that the laws of physics might not be the same everywhere is unsettling. In traditional physics, we expect that laws are universal, but in the multiverse picture created by eternal inflation, the laws might only be local. What we call the laws of nature might just be the specific settings of our bubble. In other regions, reality might follow a different script. Some physicists see this as a strength. If the multiverse contains all possible versions of physical laws, then we no longer have to explain why our universe has the exact properties it does. It just happens to be one of the many possible bubbles where life can exist. If a bubble has conditions that allow galaxies, stars, planets, and chemistry, then observers like us might arise and ask questions. This line of reasoning is called the anthropic principle. It doesn't explain the laws of nature from first principles, but it does explain why we see laws that support life. Others are uneasy with this approach. It's hard to test the multiverse directly. We can't visit other bubbles or communicate across the inflating space that separates them. Even if other universes exist, we may never be able to prove it. That raises questions about whether the idea belongs in physics or philosophy. Still, the logic of eternal inflation is hard to avoid. Once the inflaton field is allowed to fluctuate, the rest follows naturally from the math. There are a few possible ways we might detect signs of other bubbles. One is through bubble collisions. If two bubble universes formed close to each other in space, and if inflation ended in both at nearly the same time, they might have collided early in their histories. Such a collision might leave a circular scar or a region of unusual temperature patterns in the CMB. So far, no such clear signature has been found, but researchers continue to search. Another possibility comes from the overall structure of the universe. If space has a fractal nature due to eternal inflation, it might lead to subtle effects in the distribution of galaxies or the way large-scale structures form. These effects would be extremely hard to measure, and any signal would be buried in cosmic noise. Some theorists have tried to build detailed models of how eternal inflation works. These models use probability distributions to describe where and when new bubbles appear. They try to calculate how likely different types of universes are and whether certain kinds of physics are more common than others. But the infinite nature of the process makes it difficult to define meaningful probabilities. If the multiverse contains an infinite number of bubbles of every possible kind, how do you measure how likely one kind is compared to another? This is known as the measure problem, and it's one of the biggest open questions in multiverse theory. In some versions of string theory, the problem becomes even more complex. String theory doesn't predict one vacuum state but many. The number is huge, possibly 10 to the power of 100 or more different vacua, each corresponding to a different way of curling up extra dimensions or setting the values of physical constants. This vast landscape of possibilities is called the string theory landscape. Eternal inflation acts as a mechanism to explore that landscape. Each bubble universe might settle into a different part of the landscape, realizing a different version of physics. This connection between string theory and eternal inflation has led to new interest in both ideas. Some researchers see the multiverse as a natural outcome of combining inflationary cosmology with high-energy physics. Others are looking for ways to narrow down the landscape or to find selection rules that favor certain kinds of universes. But the picture that emerges is very different from the simple model of a single Big Bang followed by a smooth, expanding cosmos. Instead, we find a universe that is constantly branching, bubbling, and dividing. Our own universe is just one leaf on an enormous tree. The rest of the tree is beyond our reach, perhaps forever, but its existence may be written into the very structure of space itself. For those who study the early universe, this raises deep questions like, is our universe typical or rare? Are the laws of physics inevitable or random? Did a pre-Big Bang false vacuum ignite everything? A false vacuum is a special state that might look stable on the surface, but deep down isn't truly the lowest energy state possible. Just like water can freeze or boil under the right conditions, space could have gone through a sudden shift, changing from this false vacuum into a different, lower energy state. That sudden transition might be what ignited the hot, expanding universe we live in today. In the early stage, space would have been almost completely empty. No particles, no radiation, no stars or galaxies. Just vacuum energy, spread out evenly. But appearances can be misleading. The false vacuum might have only been metastable, meaning it was only temporarily stable. Eventually, something would push it over the edge. Imagine a ball sitting in a shallow valley near the top of a hill. It's not rolling down yet, but it's also not at the bottom. If a gust of wind or a tremor gives it enough of a nudge, the ball can tip over the ridge and fall into a deeper valley below. That's the idea of vacuum decay. The universe sits in a higher energy state until a tiny quantum fluctuation, something completely random, pushes it out. From there, the decay spreads outward at nearly the speed of light, transforming the vacuum into a new state that allows matter, radiation, and everything else we see to form. This event would release a large amount of energy, heating space and setting the conditions for the Big Bang. It would be a phase transition happening everywhere at once inside the bubble that forms during the decay. Inside that bubble, the laws of physics might change. Particles can form. Forces can split and evolve. Time, in the sense we experience it, may only become meaningful at this stage. This offers a natural way to explain how a universe could start from a very simple cold condition and then suddenly heat up into something dynamic and structured. It also avoids the need for a singularity. Instead, the beginning is more like a transformation. Space doesn't appear from nothing, it simply changes its state. This is different from the eternal inflation picture. In eternal inflation, bubbles keep forming in an inflating background, forever spawning new universes. But in the false vacuum idea, there is only one bubble. Inflation might still play a role, but it only happens after the transition begins. The emphasis is on a one-time shift, not on a never-ending process. The vacuum in quantum field theory isn't just empty space. It's a complex structure made of fields, constantly buzzing with activity even when there are no particles. In this setting, a false vacuum is like a local minimum in an energy landscape. It's not the lowest possible energy overall, but it's lower than anything immediately around it. Quantum tunneling can allow the field to pass through the energy barrier and drop into the deeper minimum. When that happens, a small bubble of the new vacuum forms and starts to expand. This bubble expansion is violent and sudden. The walls of the bubble race outward, and inside, the energy that was stored in the false vacuum gets released. That release becomes the energy that fills our universe with particles and heat. The new vacuum sets the rules for the physics that follows, what kinds of particles exist, and how the universe evolves over time. The decay of a false vacuum is a rare and random quantum event. It doesn't happen on a predictable schedule. In fact, if our universe today is still in a false vacuum, it could decay at any moment, without warning. That possibility is sometimes discussed in particle physics, especially in connection with the Higgs field. Depending on the exact mass of the Higgs boson and the top quark, some calculations suggest that the vacuum we live in today might also be metastable. If that's true, it means our universe could one day end in the same way it might have begun, with a sudden phase transition to a new state, wiping everything away in an expanding bubble. But for the early universe, the false vacuum is used as a starting point rather than an ending. Researchers try to work out what kind of field could have produced this vacuum and what its properties must have been. They also look at the temperature, energy levels, and symmetry breaking that could follow from such a decay. Some models build this into a larger framework, where the false vacuum is part of a series of phase transitions, each one reshaping the structure of space and the particles it contains. Unlike the multiverse picture, which spreads out possibilities over countless regions of space, the false vacuum model is more contained. It deals with a single transition in a single region. But that transition can still lead to great complexity. Once the vacuum decays and inflation begins, small differences in the quantum fluctuations can grow into large-scale structures. The smooth start gives way to a bumpy, clumpy cosmos filled with stars and planets. Some versions of the false vacuum idea also connect to ideas in string theory. In those versions, the vacuum corresponds to one particular configuration of the extra dimensions predicted by the theory. When the false vacuum decays, the configuration shifts, leading to a new vacuum and possibly different properties of space. The string landscape, with its enormous number of possible vacua, might offer many false vacuums to choose from. In that case, our universe might have begun in one configuration and tunneled to another, more stable one. If we could ever find evidence that our vacuum was once metastable, or that a similar decay might happen again, it would offer a powerful clue. Though there's no direct evidence yet that our universe began this way, the model remains appealing because it fits within the known rules of quantum field theory. It doesn't require inventing new types of time or space, and it avoids singularities by replacing them with transitions. In many ways, it's one of the most conservative ways to explain how a quiet, frozen start could lead to the Big Bang. The quantum foam beneath reality. In the mid-20th century, physicist John Wheeler introduced the concept of quantum foam. At ordinary scales, the universe appears smooth and space behaves in a way that makes sense. But according to Wheeler, if we could shrink ourselves down to unimaginably small scales, around what's called the Planck length, about 10 to the power of -35 meters, that smoothness would vanish. Instead of a flat or gently curving space, we would see a foaming, bubbling mess. Space and time would constantly be popping in and out of different shapes. Tiny wormholes might flicker into existence and vanish again. Distances would stop being reliable. Angles and directions would lose their meaning. The entire structure of space-time would be fluctuating like a boiling liquid. This picture comes from trying to apply quantum principles to gravity. Normally, quantum mechanics describes how particles behave in fields like electromagnetism or the Higgs field. But gravity isn't just a force, it's the shape of space-time itself. So, when you try to apply quantum rules to gravity, you end up trying to describe how the shape of space and time behaves at the smallest scales. And when that happens, things get messy. The mathematics suggests that space-time can't stay smooth and continuous at those scales. It breaks apart. Curvature fluctuates wildly. Energy levels become uncertain. Topologies might change from moment to moment. In some scenarios, you get tiny, short-lived black holes, pinched-off regions, and possibly even time loops that snap back on themselves before they can spread. Wheeler's idea was that this might be the foundation of everything. What we think of as solid, orderly space-time might just be a stable bubble that formed within this larger foam. In that case, our universe is like a brief calm patch in a sea of constant turbulence. The foam isn't made of particles, it's made of geometry itself, of the fluctuating connections and shapes that define how space stretches and bends. When quantum uncertainty is applied to those shapes, you get a restless, ever-changing structure beneath what seems fixed and solid. And like the bubbles in boiling water, one of these fluctuations could have, by chance, reached a stable state. That fluctuation might have expanded, smoothed out, and become the universe we live in. False vacuum or inflation models still assume a kind of structure, fields, symmetry, energy levels that exist in a framework that makes sense. Quantum foam, in contrast, offers a picture where structure itself is a lucky outcome. There's no background space into which the universe expands. There's no time that ticks before the bubble forms. There's just foam, seething and unpredictable. One reason physicists take this seriously is that general relativity and quantum mechanics, when pushed to the limit, force us to think this way. If you try to describe a gravitational field using quantum principles, you quickly run into mathematical inconsistencies. Space and time, as described by general relativity, are continuous. But quantum mechanics deals with probabilities and uncertainties. Mixing these together breaks the logic of both. The result is a picture where smooth space can't survive at very small scales. Something else must take its place. Various attempts to fix this problem have led to candidate theories of quantum gravity, like LQG, string theory, and causal dynamical triangulations. Many of these theories agree that space-time has a granular or discrete structure at the Planck scale. They just differ in how that structure works. But Wheeler's idea goes a step further. It doesn't just suggest that space-time has structure at small scales. It suggests that this structure is unstable and wild, that there's no order at all until a fluctuation brings it about. If this is true, then what we call the universe is just one rare bubble of stability in a deeper background of chaos. In this sense, our entire reality might be like a stable soap bubble floating in boiling water. Most of the foam never forms anything lasting, but once in a while, a large enough fluctuation creates a patch of space that doesn't collapse right away. That patch grows, maybe even becomes infinite from the inside, and takes on the qualities we recognize as a universe. Within that bubble, space is smooth, time flows in one direction, and physics can operate in a predictable way. But outside that bubble, if outside even makes sense, there is no such order. There's no space, no direction, no cause and effect as we understand them. Just constant, seething uncertainty. This is not something we can observe directly. Our instruments and measurements depend on being within stable space and time. They don't work outside of those conditions. But the idea remains important by challenging us to rethink what kind of structure underlies everything. One challenge with quantum foam is that it's incredibly hard to model. We can guess at its properties, and we can look for signs that space-time has limits to how small we can measure. For example, some researchers have looked at how light from distant stars and galaxies might be slightly distorted if space-time is grainy at very small scales. Another angle comes from black hole physics. When you get close to the event horizon, space-time becomes extremely curved. This creates a setting where quantum effects on gravity might show up. Some researchers believe that studying how black holes evaporate could give hints about the structure of quantum foam. Quantum foam remains one of the boldest attempts to think about how space-time itself could come from something deeper. Even now, beneath the smoothness of everyday space, that foam might still be churning, too small to see, too fast to measure, but always there. Are gravitational waves a window into pre-Big Bang events? First predicted by Albert Einstein. More than 100 years ago, gravitational waves remained an idea until they were directly detected in 2015. That detection came from the collision of two black holes more than 1 billion light-years away. The waves from that event reached Earth as tiny shifts in the length of laser beams inside long detectors. It was a moment that confirmed one of the most subtle parts of Einstein's theory of gravity, that space-time itself can move. But while collisions like those produce gravitational waves we can already detect, scientists are also searching for another kind, much older, far weaker, and spread across the entire sky. These are called primordial gravitational waves, and they may have formed in the earliest moments of the universe, possibly even before the Big Bang as we usually define it. Gravitational waves differ from light. They don't scatter off particles, they don't get absorbed by matter. Once created, they pass through everything, barely disturbed. That makes them perfect messengers from deep time. While light from the early universe gets blocked or blurred by hot plasma, gravitational waves pass through that chaos untouched. In theory, they could carry information from the very first fraction of a second, or even earlier. The most talked about source of primordial gravitational waves is cosmic inflation. Inflation didn't just stretch matter, it also stretched space-time. That stretching would have produced gravitational waves that spread out along with everything else. If those waves still exist, they would leave a faint signature in the CMB. We've mapped tiny temperature differences across the CMB, but gravitational waves would leave a more subtle mark, a twisting pattern in the polarization of the light called B-mode polarization. Experiments like BICEP, the South Pole Telescope, and the upcoming LightBird satellite are all searching for these twists. The signal is expected to be weak, and there are other effects, like cosmic dust, that can mimic it. But if scientists do find a true B-mode signal, it could tell us about what happened just a tiny fraction of a second after the Big Bang. These primordial gravitational waves might even carry traces of what happened before inflation. If the universe went through a false vacuum decay phase, that kind of transition, if violent enough, would have shaken space-time and produced gravitational waves. If the universe cycled through contractions and expansions, the bounce from one phase to another might also produce a burst of gravitational radiation. Or quantum fluctuations in the pre-inflationary state could have been large enough to send ripples through the geometry of space. If those ripples survived, they would show up today as a background hum. Very quiet, but still there. To detect such a signal, scientists rely on extremely sensitive tools. Detectors like LIGO and Virgo can already hear strong signals from black holes and neutron stars, but primordial waves are much weaker and have different frequencies. Future observatories like the space-based Laser Interferometer Space Antenna, or LISA mission, will listen to lower frequencies than LIGO can reach. Other projects, like pulsar timing arrays, use the regular flashes of radio waves from distant stars to look for slow, sweeping gravitational changes across the galaxy. If a background of primordial gravitational waves is found, scientists can analyze the shape of the signal, its spectrum. Different events produce different patterns. A sudden vacuum decay would create a sharp burst. A slow transition might leave a smoother signal. Inflation itself is expected to produce a certain tilt in the spectrum, depending on how the inflaton field behaved. By measuring this tilt, scientists can narrow down the kind of inflation that may have taken place, or whether something else happened entirely. There are also other ways gravitational waves could carry echoes of creation. Some models predict that defects in space, such as cosmic strings, might have formed early on. These are not strings like in string theory, but narrow lines of energy left behind by broken symmetries in the early universe. If they exist, they could vibrate and loop around, producing bursts of gravitational waves. These bursts would be spread out in time, and their presence would suggest a very different picture of the early cosmos. In certain theories, gravity can leak into other dimensions of space, ones that we don't experience directly. If that happened during the early universe, it could affect the way gravitational waves formed and moved. Some energy might have been lost into those dimensions. Some waves might have different properties than expected. By measuring how the waves behave, scientists can test whether our universe is really four-dimensional, or if there's something more beneath the surface. Because gravitational waves interact so little, they can survive journeys of billions of years. But that also makes them hard to find. Their signals are weak. They get buried in noise. It takes years of data, careful filtering, and the cooperation of multiple observatories to extract a possible signal. Even then, false positives are a risk. The history of gravitational wave searches includes many hopeful moments followed by corrections. Still, they are important because they offer a way to observe what no telescope can see. Light can only take us back so far. After that, space was too dense, too hot, too foggy for photons to move freely. But gravitational waves can reach past that fog. They come from the fabric of reality itself, offering a direct link to the origins of everything. The conformal cyclic universe. Did time loop around to start again? The conformal cyclic cosmology, or CCC model from Roger Penrose, proposes that the universe is not a one-time event. Instead, it is made of a series of phases, which Penrose calls eons. Each eon starts with something like a Big Bang, expands for an incredibly long time, and eventually becomes cold and empty. But rather than ending in silence, Penrose suggests that this final state of one eon can be mathematically transformed, or conformally mapped, into the beginning of the next. The word conformal means that angles are preserved, but distances and sizes are not. In conformal geometry, the scale of objects can be shrunk or stretched, but their shapes and the way they relate to each other stay intact. This is important because it lets you connect the extremely large with the extremely small, without needing to pass through a physical point like a singularity. Penrose's key insight is that as the universe expands over trillions upon trillions of years, all matter eventually decays. Black holes evaporate through a slow process called Hawking radiation. Particles lose energy. Stars go out. What's left is a thin, featureless sea of radiation and space. In that final state, there's no more mass. And when there's no mass, there's no way to measure scale in any meaningful way. Everything becomes scale-free. That's the point where conformal geometry comes in. Because the universe becomes scale-invariant, Penrose argues, you can mathematically shrink it down to a kind of boundary. That boundary doesn't have sharp edges or a singularity like the traditional Big Bang. It's smooth, empty, and timeless. And that boundary, according to the CCC model, is the Big Bang of the next eon. In other words, the end of one universe leads naturally into the beginning of another, through a shift in how scale is understood. The direction of time continues in the same way, but the physics resets. A new era begins with a new low-entropy starting point. Traditional bounce models imagine the universe contracting under gravity and then rebounding due to quantum effects. In those cases, time can reverse direction or loop back through a minimum point. But the CCC doesn't rely on contraction. It assumes eternal expansion. The change happens not through forces or energy, but through geometry. This model is that it doesn't depend on adding extra dimensions, speculative fields, or exotic physics. It mostly uses general relativity and ideas about massless particles in an expanding universe. Penrose argues that once all particles become effectively massless, as they do when everything decays, then conformal geometry becomes a natural way to describe space and time. Still, the idea is bold and not widely accepted. If eons are separated by such vast stretches of time, it's hard to imagine any signal surviving from one to the next. But Penrose believes there might be clues. He has proposed that radiation from events in the previous eon, particularly collisions between supermassive black holes, could leave marks in our own. These marks would appear as concentric circles with lower temperature variation than the surrounding regions. Penrose and his collaborators have claimed to find such circles in satellite data, but their interpretation is controversial. Other teams have looked at the same data and found no strong evidence that these patterns are anything more than random noise. Still, the idea remains appealing to some because it avoids one of the most uncomfortable features of standard cosmology, the singularity. Many theories try to avoid the singularity by introducing quantum corrections, new dimensions, or other mechanisms. The CCC model takes a different route. It redefines the boundary between eons so that no singularity is needed at all. If time can loop in this way, if eons follow each other forever, then what does that mean for causality? Are we living in just one of an endless sequence of universes, each giving rise to the next? Could some form of information, energy, or even structure pass through the boundary from one eon to the next? Penrose has suggested that the answer might be yes, at least in a limited sense. If some features of the past universe are encoded in massless radiation, they might cross the conformal boundary. That would mean our universe, though new in its matter and structure, might carry echoes from a cosmos that lived and died long before our own began. There's also a curious twist in the way the CCC model handles entropy. Usually, entropy increases over time. In the early universe, entropy was low. In the far future, entropy is high. But if the universe ends in a smooth sea of radiation with no structure, is that maximum entropy or minimum entropy? Penrose argues that in conformal terms, it's more like a new beginning. Because everything is massless and structureless, the entropy resets, and a fresh arrow of time can begin. It's unclear yet whether the CCC model will hold up to future data. It may turn out to be a beautiful idea that doesn't match our universe, but it raises useful questions about what it means for time to end, and whether the Big Bang is a boundary or just a hinge between worlds. Brains in collision, the ekpyrotic scenario, and a universe born from dimensional impact. In string theory and its broader framework known as M-theory, the basic idea is that what we consider to be the universe may be just a small slice, a membrane or brain, floating in a much larger and more complex space. These brains can have many dimensions, including extraspatial ones that we don't experience directly. In this ekpyrotic scenario, things begin with a very different kind of event, a collision between brains. The term ekpyrotic comes from a word in ancient Greek philosophy, referring to a periodic destruction and rebirth of the cosmos through fire. That name was chosen deliberately because the scenario describes the birth of the universe as the result of a fiery impact in a higher dimensional setting. The basic framework of the ekpyrotic model starts from the idea that our universe is a three-dimensional brain embedded in a higher dimensional space. In this space, there may be other brains as well. These brains carry energy and tension, and they can move, stretch, and interact. According to the model, our universe began when two such brains, floating in a higher dimensional bulk, approached one another and eventually collided. This collision would become the cause of the hot, dense state we associate with the Big Bang. The singularity is replaced with a more controlled transition. When the brains hit, energy was transferred from the motion of the brains into the matter and radiation that would fill the newly born universe. The expansion that followed was not the beginning of space, but a transformation of energy states. This offers a different solution to certain long-standing puzzles like the flatness problem and the horizon problem. These are usually handled by inflation, but the ekpyrotic model tries to solve these same problems by using a period of very slow contraction before the collision. In this pre-collision phase, the universe doesn't grow rapidly. It shrinks in a very smooth and stable way. This phase of slow contraction acts to smooth out inhomogeneities and flatten out any spatial curvature. By the time the brains collide, the conditions are already set up to create a nearly uniform universe. That removes the need for inflation altogether, or at least allows for alternatives to it. And because there is no singularity, the equations of physics don't break down in the same way they do in general relativity at time equals to zero. The actual mechanism behind the brain collision is based on higher dimensional dynamics. In M-theory, which includes 11 dimensions, the kinds of objects involved, membranes and extended surfaces, are fundamental building blocks. These brains can carry fields that live only on their surfaces, and those fields may look to us like the particles and forces of the standard model. But gravity can propagate through the higher dimensional bulk as well. That's how the brains can see each other, through the exchange of gravitational influence, or possibly even through direct interaction via bulk fields. However, these extra dimensions involved are not visible to us. They may be compactified or wrapped up so tightly that we don't notice them in ordinary life. But the physics that takes place in those extra dimensions could still leave imprints in our own. In some versions of the model, the brane collisions aren't just a one-time thing. Instead, the universe might go through repeated cycles of brane separation, contraction, and recollision. This idea is sometimes called the cyclic ekpyrotic model. Each brane collision creates a new hot Big Bang-like phase, followed by expansion and eventual cooling. As time passes, the branes drift apart again, and then the whole process starts over. Unlike traditional bouncing cosmologies, this version sees the branes as constant entities moving in a fixed background, with their interaction driving the observable cycles. Even when the branes come together, the description of space doesn't collapse to a point. Instead, the extra dimensions remain intact, and the collision simply alters the energy content of the branes. In theory, this might allow for a continuous history of events stretching backward far before our own universe began. Modeling the collision precisely is not easy. The equations that govern brane interactions in string theory are complex, and in many cases not fully understood. There's also uncertainty about how the collision energy is converted into the particles and radiation we observe. The theory must find a way to match the fine details of the early universe, its density, its temperature fluctuations, and its composition, if it is going to be considered a complete alternative to inflation. Some physicists worry about the amount of fine-tuning required. The branes must approach each other in a very specific way, with the right timing and energy, for the universe to emerge in a form that looks like ours. Small deviations could lead to wildly different outcomes, or no outcome at all. If the ekpyrotic scenario is right, why did the branes behave the way they did? Is there some underlying reason for their alignment, or is it just one possibility among many? The ekpyrotic model provides a framework in which space and time are not absolute, but emergent features of a deeper and more complex setup. This kind of thinking opens up new ways to imagine the past. The higher dimensional space itself could be timeless or governed by rules that are very different from the ones we experience. As with many ideas in modern cosmology, the ekpyrotic model is still being refined. There are competing versions, and some incorporate elements from quantum gravity or string compactification schemes. It stands out due to its geometric picture of origins, not as a point, but as an interaction. A universe without a bang. Could the cosmos have emerged gradually without a singularity? Instead of beginning in a bang, the universe may have emerged slowly, carefully, and without ever passing through a point of infinite density. This is the basic idea behind what are called emergent universe models. These models suggest that time stretches far into the past, possibly forever, and that the universe existed in some calm, quasi-static or slowly evolving state before becoming the expanding cosmos we see today. In this picture, there is no singular beginning. The geometry of space doesn't shrink down to zero, and there is no moment when the curvature becomes infinite. Instead, the universe hovers for a long period near a minimum size. Then, under the right conditions, it begins to expand. The expansion is smooth, continuous, and controlled. It is driven by a change in the internal dynamics that slowly pushes the system away from equilibrium. One early version of this idea goes back to models where the universe is static or nearly static in the distant past. Instead of nothingness, there is a universe that exists in a steady state, perhaps filled with a scalar field and low-density radiation. For a long time, this configuration remains stable. Then, something causes the balance to tip. The field begins to roll, slowly at first, and then more quickly. This rolling field behaves like a kind of clock, triggering an eventual phase transition that causes inflation or expansion to begin. The beginning is not a sharp boundary. There's no instant when we can point and say, "This is when time began." Instead, time just keeps going further back. The early state of the universe may have been very small, but not zero. Its curvature may have been large, but not infinite. There is no wall that separates existence from non-existence. From a mathematical perspective, These models often involve solutions to Einstein's field equations that avoid singularities by including additional fields or by modifying gravity slightly at very high densities. One commonly used feature is a scalar field with a carefully chosen potential that can maintain a steady state for long periods. This field acts like a cushion, holding the universe in balance until it begins to change. Some versions of the theory also include quantum corrections, but these are added in a way that supports a smooth evolution rather than triggering a tunneling event or bounce. Where inflation starts with a violent exponential push, the emergent universe starts with a whisper. The early conditions are calm, nearly timeless. The universe may have been much smaller than today, but it wasn't collapsing. It simply sat in a state of quiet balance until the slow dynamics pushed it into motion. This approach avoids the need for a quantum gravity theory at the earliest moments. If the universe never reaches infinite density and never passes through a true singularity, then the equations of general relativity remain usable all the way back. This makes the model simpler to analyze. It also allows physicists to make testable predictions without relying on unknown physics. For example, the early universe in these models is often assumed to have a nearly constant size for a very long time. That stable size sets the stage for a certain kind of symmetry and energy distribution. As the universe eventually begins to grow, those initial conditions can shape the types of structures that later appear. The spread of galaxies or the smoothness of space might carry traces of this slow beginning. In some cases, the expansion from this minimum state leads into a short period of inflation, similar to what other models predict. But inflation is not the trigger for creation, it's just one phase in a longer ongoing history. This gives the emergent universe the ability to include the benefits of inflation without needing a bang to set it off. There are versions of the model where inflation is completely eliminated. The early, slow growth phase may be enough to explain the observed flatness and homogeneity of the universe. If the universe existed for an extremely long time in a nearly static state, even tiny processes could eventually smooth out irregularities. The energy of the scalar field can remain nearly constant, acting like a cosmological constant that eventually begins to dominate and drive expansion. This allows the universe to appear to start expanding without ever having to start in the traditional sense. One problem with this model is stability. Holding the universe in a steady, balanced state for a long time requires a fine-tuned configuration. Small perturbations could cause the system to collapse or expand prematurely. The scalar field and its potential must be chosen with great care to allow for such a prolonged and stable state. If the potential is too steep, the field rolls too quickly and inflation begins too soon. If the field is too flat, nothing ever changes. Another issue is entropy. If the universe has existed forever in some form, where did all the entropy go? In other models, the universe starts in a low entropy state, but if the emergent universe has no beginning, we must explain how entropy stays low enough for structure and order to eventually form. Some versions handle this by assuming that entropy production is limited during the early static phase. Others suggest that entropy was somehow reset or never accumulated much in the first place. There's also the question of how the emergent state begins. If the universe existed forever, then we're back to asking why this specific state existed for so long. What selects the field, the geometry, or the matter content of that early state? These are open questions. And like many areas of cosmology, the answers may depend on physics we don't yet understand. But the difference here is that the unknowns are layered on top of a known background, the steady universe. Some scientists are working to build detailed simulations that can compare the predictions of emergent models with the data we get from space telescopes and surveys. If the signature patterns match, it could offer support for a universe that grew into being rather than appearing suddenly. This view may not have the dramatic flair of other origin stories, but it offers a sense of calm continuity. In a field filled with bangs, bounces, and bursts, that quiet persistence makes the idea stand out. Black hole genesis. Was our universe born in a higher dimensional black hole? What if our entire universe is the inside of a black hole? More specifically, what if our Big Bang was the birth of a universe formed within a black hole that exists in a larger, higher dimensional reality? This idea proposes that our expanding universe came into being from the gravitational collapse of matter in a higher dimensional space. In that space, sometimes imagined as having 5 dimensions instead of 4, a massive star or region of dense matter collapsed under its own gravity, forming a black hole. But rather than leading to a dead-end singularity, as happens in our own universe's black holes, the interior of this higher dimensional black hole could instead contain a new expanding universe. In that sense, our universe would be a kind of cosmic offspring, a baby universe born from the gravitational death of something in a higher world. In general relativity, the equations that describe black holes and the equations that describe expanding universes are more closely related than they first appear. In both cases, extreme curvature in space-time plays a central role. In fact, if you move through the math and change the sign of certain terms, a collapsing object in one frame can become an expanding universe in another. What looks like a singularity from one point of view can look like a beginning from another. The difference comes down to how you define time and how the geometry is laid out across dimensions. Inside a black hole, the roles of space and time are flipped. In a normal setting, time flows forward and space is laid out in 3 directions. But inside the event horizon of a black hole, the flow of time points inward, toward the center, and there's no way to stop the fall. In that sense, moving deeper into the black hole becomes a kind of unavoidable future. This reversal opens up a new way of thinking. What if the direction we experience as forward in time is actually the direction someone in a higher dimension would call inward toward the singularity? If that's the case, then the Big Bang, the place where our time starts, would be the point at which matter from a parent universe fell into a black hole and crossed over into a new region where the geometry was completely different. In the simplest form of this idea, imagine a 5-dimensional universe where black holes form in much the same way they do in our own. But in that universe, when matter collapses, the interior region doesn't just stop at a point of infinite density. Instead, it creates a kind of funnel or bridge, a throat that leads to a new spacetime on the other side. On our side of that throat, everything is expanding. The geometry is smooth, and time begins to flow outward. This concept borrows from and overlaps with ideas from string theory and brain cosmology. But in the black hole genesis picture, the bulk is dynamic and filled with objects capable of collapsing, forming black holes, and birthing new regions. Our brain could have been formed inside one of those black holes, with the dimensions curled or warped in such a way that we only experience 4 of them. From the outside perspective, in the higher dimensional space, the black hole would look like a standard object, massive, with a powerful gravitational field. But to someone on the inside, in the new universe created by the collapse, there would be no visible connection to the parent world. Instead, the early universe would appear hot, dense, and rapidly expanding, just like what we observe from our side. In normal black hole physics, the event horizon hides information about what fell in. Everything that enters becomes smoothed out, and the interior appears nearly uniform. This smoothing could carry over to the birth of a new universe. The collapse in the higher dimensional space may have filtered and organized the incoming matter in a way that left the interior, our universe, with the precise conditions needed for stars, galaxies, and eventually life. Some versions of this idea include a phase of rapid early expansion, driven by the geometry of the black hole's interior. Others suggest that inflation is not needed at all because the collapse itself already sets the stage for the observed features of the universe. The shape of the throat, the rate of expansion, and the curvature of spacetime could all emerge naturally from the higher dimensional geometry. They offer new paths for linking theoretical physics with cosmological observation. We can't travel to the edge of the universe to look for an event horizon, and we can't communicate with the parent universe, assuming it even exists. But there may be indirect clues. For example, the structure of cosmic expansion might carry subtle clues of the initial conditions set by the black hole collapse. If our universe is a bubble growing inside another space, then what happens when we form black holes in our own universe? Could they also spawn new regions of space-time? Could every black hole we see be the beginning of a new universe, hidden behind the veil of its event horizon? Some physicists have explored this idea, proposing that our universe might be part of a long chain, each born from the collapse of a black hole in the universe before it. In this picture, black holes are not just the endpoints of stars, but are the engines of creation themselves. It's a bold idea, and like many bold ideas in cosmology, it walks the line between what can be described by equations and what remains speculative. But Einstein's equations allow for these kinds of transformations. They allow for regions of space where time flows in unexpected ways and for boundaries between different kinds of geometry. The key is to find the right framework, a combination of general relativity, quantum field theory, and higher dimensional physics that brings it all together. Could the Big Bang be a white hole's death cry? If black holes are known for pulling everything inward, then white holes are their mirror opposite. Nothing can enter a white hole, and everything inside it is forced out. Matter and energy come flying out from a single point, pushed away by a powerful burst. In terms of the math used in general relativity, a white hole is simply a time-reverse version of a black hole. Where a black hole draws in, a white hole expels. And for some scientists, this rare solution in Einstein's equations might hold the key to the Big Bang. Instead of being a place where gravity crushes everything to an infinite point, a white hole begins with everything already packed tightly together and then violently flung outward. From the inside, it would feel like time is moving forward. From the outside, it would look like a singular eruption of space and energy. It wouldn't last long. It would act as a one-time burst, then disappear. That description sounds a lot like the Big Bang. This connection has led to the idea that the Big Bang could have been a white hole, not just similar to a white hole, but actually behaving as one. The universe may have started as the final act of a white hole's brief existence. A single burst of energy and structure expelled from a point in space-time. Black holes are solutions to Einstein's field equations. So are white holes. Mathematically, they are mirror images, created by reversing the direction of time in the equations. And since general relativity does not place a fundamental arrow on time, it allows things to run backward in its purest form. Then a white hole should be just as valid as a black hole. The reason we don't see them might have more to do with entropy and thermodynamics than with the math itself. Instead of collapsing into a state of higher entropy, the white hole starts with incredibly low entropy, everything packed together and highly ordered, and then erupts outward, spreading that energy and structure. This fits surprisingly well with our early universe. This theory doesn't answer all the problems, of course. For one, no one has ever seen a white hole. They remain purely theoretical. In contrast, we have observed black holes directly, seen their shadows, tracked their gravitational pull, and watched stars being torn apart at their edges. White holes, by their nature, would appear and vanish too quickly to spot, or they might only exist in very rare or early cosmic conditions, long before any observer could have recorded them. If the universe itself is the aftermath of a white hole, then we wouldn't be able to see it from the outside anyway. This approach bypasses some of the deeper issues in other cosmological models. Many theories introduce new particles, new dimensions, or parallel universes. But the white hole idea doesn't need any of that. It doesn't change the physics, it simply reverses it. It asks what would happen if we looked at the universe's birth not as a one-time miracle, but as a natural consequence of time flowing the other way. Some physicists speculate that every black hole could lead to a white hole in another realm, or perhaps even in another time. If time flows inward in a black hole, maybe it continues on and then flips into outward flow again, creating a new universe on the other side. Black holes might take in stars, planets, and gas, compress them beyond comprehension, and then, on the other side of time, release that energy into a new realm. Our own universe could be the product of such a transformation, a white hole born from the ashes of something else. There are some versions of this idea that try to work backward from observations. Instead of starting with equations and speculation, they ask what features of the early universe match the profile of a white hole event. These could be side effects of a one-time expulsion, where everything began at a single point and then expanded outward in perfect symmetry. Another subtle clue comes from the way the universe's expansion is accelerating. Dark energy, the mysterious force causing that acceleration, might relate to the final fading pressure of a dying white hole. As space stretches further and further apart, perhaps we are still feeling the aftershock of that original expulsion. The burst may be long over, but its signature may still be written into the fabric of space-time. Some theorists have begun crafting exact solutions in general relativity that describe this process. They show how a collapsing region in one part of space-time can lead to an expanding region in another. These models aren't widely accepted yet, and they often face resistance because they challenge the standard narrative. But the solutions don't break the known laws. They simply twist them in a new way. The Big Bang in this framework isn't a special case, just one possible outcome of a system that works both ways in time. Before everything, there were many pre-Big Bang multiverse models. Imagine a vast, perhaps endless landscape of other universes, each separate, each complete in itself, and each with its own story. This is the idea behind pre-Big Bang multiverse models. Not only does our universe have a beginning, but it may also be just one of many such beginnings, playing out across a deeper and more layered reality. These models come in several kinds, each adding a different layer of possibility. The simplest kind starts with a straightforward idea. If space is infinite, and if the laws of physics are the same everywhere, then every possible arrangement of matter must happen somewhere. It's a strange consequence of infinity. Just as every possible number exists on the number line, every possible configuration of particles should exist in a never-ending, repeating pattern in an infinite cosmos. In this version, the Level 1 multiverse, there are copies of you, of Earth, and of everything else, simply because randomness combined with infinity must eventually loop. This model just extends what we already know. Space is big, and if it goes on forever, then repetitions are inevitable. You would never reach one of these identical or nearly identical Earths because they would be unimaginably far away, past the visible edge of our universe. But in principle, they could exist. And if our own observable universe began with a localized Big Bang, it might be just a piece of this greater whole, like one bright patch in a much larger quilt. The Level 2 multiverse takes a step further, with the idea of eternal inflation. Each inflating pocket becomes its own universe, with its own Big Bang and its own physical properties. The field driving inflation can settle in different states in different regions. These states determine what kinds of particles and forces are allowed. Some universes may have no stars, others may have different numbers of dimensions or altered versions of gravity. The Level 2 multiverse doesn't just repeat outcomes, it explores different versions of the rules themselves. Beyond these, there's Level 3. This is the multiverse that arises from quantum mechanics. In standard quantum theory, particles can exist in many possible states at once, what's called a superposition. But when we observe a particle, we see only one outcome. According to one interpretation, called the many worlds view, every possible outcome actually happens, but in different branches of reality. Every time a quantum choice occurs, the universe splits. There is a branch where the particle goes left and one where it goes right, a branch where the cat lives and one where the cat dies. In this picture, every possibility becomes real, not in distant space, but in separate versions of reality stacked beside each other. This model suggests that the universe didn't begin from a single timeline, but has been branching constantly since its beginning. And if these branches go backward as well as forward, then maybe there wasn't just one quantum history before our Big Bang. Maybe there were many, each feeding into our own present. This would mean that our universe emerged as one strand among a thick web of quantum paths. Even before time as we know it began, this framework says that possibility itself was already spreading outward, splitting reality into pieces. Finally, there's level 4. This is the most extreme version of the multiverse. It proposes that every possible mathematical structure corresponds to a real universe. If a system can be defined logically and consistently, then it exists, not just as an idea, but as a physical reality. In this model, our universe is just one example of a mathematically possible world. Others could obey entirely different logics, different kinds of space, different numbers, even different definitions of causality or time. Most of these would be completely alien to us, but they would be just as real, in a broader sense. If math is discovered rather than invented, and if the universe itself can be described by math, then maybe everything that can be described mathematically exists somewhere. There would be no need for a single origin or a preferred set of physical laws. The idea of beginning loses its meaning because every possible form of existence would already be there in this limitless library. All of these multiverse models, levels 1 through I Voy, offer different pictures of what came before or beyond our own universe's start. Some are based on known physics, others are more philosophical. Each level builds on the previous one. First, you get many regions in infinite space. Then you get separate universes with different physics. Then you get quantum splits producing new realities. And finally, you get the full space of all mathematically possible worlds. They don't all need to be true at once. But if even one of them is right, then the idea of our universe being the whole story is no longer sustainable. Did our universe tunnel into existence? In the early 1980s, physicists like James Hartle, Stephen Hawking, and Alexander Vilenkin began exploring how quantum rules might apply to the birth of the cosmos. The key idea is this: if you can talk about a particle tunneling into existence, appearing in a new place even if it had no classical way to get there, then maybe a whole universe could do the same thing. In quantum physics, tunneling happens when a particle has a certain chance of passing through a barrier that it couldn't cross under normal rules. It doesn't climb over the hill. It simply appears on the other side without violating the laws of physics. Alexander Vilenkin's proposal is based on this idea. He imagined a scenario in which the universe begins as a quantum fluctuation. There's just the nothing from which something can emerge. Not an empty space, not a vacuum, but the total absence of physical existence. From this nothing, the universe tunnels into being. It doesn't need a cause in the traditional sense. It simply has a tiny probability of coming into existence. And once it's here, quantum fluctuations drive rapid expansion, which turns the tiny beginning into the vast cosmos we observe. Vilenkin's model paints a picture that is hard to grasp in everyday terms. There's no time before the universe because time begins with the universe. There's no outside space where the universe appears because space also begins at that moment. It's not that the universe pops into some pre-existing container. It's that the very fabric of space-time springs into being as a quantum event. And the laws of quantum mechanics, being mathematical, don't require a background in which to operate. They can, in a way, write themselves into existence. There's a related approach proposed by James Hartle and Stephen Hawking, called the no-boundary proposal. This one takes a different route, but arrives at a similar place. Instead of imagining the universe tunneling from nothing, they describe a kind of quantum geometry that has no sharp beginning. Think of the Earth's surface. There's no edge at the South Pole. It's not that the Earth stops there, it just curves smoothly. Hartle and Hawking applied this idea to time. In their model, time behaves like a spatial dimension at very small scales. At the beginning, it curves inward like the surface of a sphere. There's no starting point with infinite density. Instead, there's a smooth transition from a timeless quantum state into classical time. In both of these models, the laws of quantum physics and the mathematical rules of general relativity adapted to a quantum setting are enough to describe a scenario in which something comes from nothing. There's a small but non-zero chance for a universe to appear. And once it does, inflation rapidly takes over, making it grow and evolve into something complex. One of the strange things about these ideas is that they can, in principle, make predictions. Even though they describe the birth of the universe from nothing, the structure of the resulting universe depends on details of the tunneling process. Different quantum rules produce different kinds of universes. Some might be flat, some curved. Some might be filled with matter, others with energy fields. The fact that our universe looks the way it does, smooth, flat, filled with galaxies, suggests that certain kinds of quantum birth are more likely than others. In this way, cosmologists can test these ideas. Of course, this approach is full of unknowns. It relies on a theory of quantum gravity which doesn't yet fully exist. The no-boundary and tunneling proposals are based on approximations, on ways of applying known physics to a realm where the rules are still being worked out. But they provide a starting point to think about the origin of the universe using the language of modern physics. Is there really such a thing as true nothingness? Or is it just the absence of space and time as we understand them? If universes can tunnel into existence, how often does this happen? And if the laws of quantum physics allow for this, why do they exist in the first place? These are questions that go beyond what science can answer right now. But quantum cosmology gives us a way to ask them, as part of a framework that ties into what we know about the universe. False vacuum decay and the dangerous possibility of a cosmic reset. The discovery of the Higgs boson in 2012 brought the false vacuum decay discussion into real terms. The Higgs field gives particles their mass, and its value determines many properties of the universe. When scientists plugged the measured Higgs mass into equations, along with the known mass of the top quark, they found something surprising. The numbers suggest that the Higgs potential, the shape of the energy curve, might not be at a true vacuum. Instead, it might be hovering in a false vacuum, sitting in a local dip on a slope that descends further into a deeper, more stable state. This means our universe might not be permanently safe. It might eventually decay into the true vacuum. If it did, the laws of physics inside that bubble would be different. That bubble would then expand outward at the speed of light, eating through the universe like a flame burning through dry paper. Anything caught in the path would stop existing according to our physics. The vacuum state of the universe would change, along with the constants that control everything from gravity to electromagnetism. Atoms wouldn't form the same way, if they formed at all. Chemistry would collapse. There would be no survivors, no signals sent, no warning. The very fabric of our reality would be rewritten in an instant. Just like a particle can suddenly appear on the other side of a wall it shouldn't be able to cross, a bubble of lower vacuum can appear within the higher vacuum of our current universe. The chances of this happening are extremely low. The odds are so small that even in a universe as old and vast as ours, no such bubble has appeared so far. But the possibility is there, and if it ever happens, we wouldn't see it coming. There are other factors that might influence whether such a vacuum decay is possible. The shape of the Higgs potential can be modified by unknown physics at high energies. If we eventually discover new particles or forces beyond the standard model, they might stabilize the vacuum. Alternatively, they might make it even less stable. Right now, we don't know enough to say for certain. But the discovery of the Higgs was a major clue, and it's one of the reasons scientists continue to study it closely, looking for small signs that could reveal the deeper structure of the vacuum. There are also theories involving multiple vacua, many valleys in the energy landscape of quantum fields. Some string theory models suggest that the vacuum structure is like a landscape with billions of possible valleys. In that picture, vacuum decay could lead not to a single new universe, but to a chain of transitions between many different vacua. Each time, the laws of nature shift and a new version of the cosmos appears. Some might wonder whether such a bubble could start somewhere else in the universe, and reach us later. The truth is that it doesn't matter where it begins. Because the bubble would expand at the speed of light, we wouldn't see it coming. No telescope could detect it in advance. It would reach us at the same moment we realized it had started. And because time and space inside the bubble behave differently, there would be no outside observers once the wave passed through. The story would end because the book itself would disappear. Most calculations suggest that vacuum decay, if it's possible at all, won't happen for trillions upon trillions of years. The universe would grow cold and dark from ordinary processes long before the vacuum drops to a lower state. Black holes will evaporate, galaxies will drift apart, and still the false vacuum might persist, holding everything together even as the lights go out. But the possibility remains. The vacuum we depend on could, one day, vanish. Not from wear and tear, but from the silent mathematical chance that the ground beneath existence will change. Could the arrow of time reverse? Mirror universes and bidirectional entropy. Some researchers have proposed models in which the universe didn't just start with low entropy and move forward. Instead, it branched out in both directions from a shared low entropy beginning. In this picture, the Big Bang, or whatever event came before, wasn't the start of time. It was a central point, a kind of turning post. On either side of that post, time flows outward, but in opposite directions. In one half of this universe, time moves the way we know it. Entropy increases, stars form and die, and intelligent life eventually looks back and asks questions. But in the other half, time flows the other way. Entropy also increases, but from the shared low point, it increases in the opposite direction. If someone lived in that other half, they would see themselves as moving forward in time just like we do. Their memories would form in what we'd call the past, and their future would look to us like our past. But from their point of view, everything would feel normal. One of the biggest puzzles in physics is why the early universe had such low entropy. That low entropy beginning is what gives our universe its arrow of time. But why was it low in the first place? Most states the universe could have started in would have been high entropy. The odds of beginning with such order are vanishingly small. Some physicists, like Sean Carroll and Julian Barber, have suggested that maybe we're thinking about the problem backward. Maybe the low entropy beginning wasn't chosen at random. Maybe it's a natural feature of a deeper kind of time, one in which the universe grows outward in both directions from a middle. Think of it like this. Imagine throwing a ball straight up into the air. At its highest point, its motion pauses for a split second. That moment is special. It's the turning point between the rise and the fall. If you didn't know which way time was flowing, you couldn't tell just by looking at the top of the ball's arc. It's symmetric. Now imagine the universe doing something similar. Not with position, but with entropy. There's a middle point where entropy is lowest, and from there it grows in both directions. Each side of the timeline sees increasing disorder. Each side sees time moving forward, but together they form a whole that's symmetric around that central point. This is the idea behind some time-symmetric cosmologies. In these models, the universe is eternal, but the arrow of time is not. It emerges locally and flows outward. That state might look like a Big Bang to us, but to someone on the other side, it might look like their Big Bang too. This leads to the idea of a mirror universe. Not necessarily one with backward physics or reversed particles, but one with a reversed arrow of time. From our point of view, that universe would look like it's running backward. But to its inhabitants, their experience of time would be just like ours, only flipped. If this model is right, then our universe might be one half of a larger whole. It's important to understand what this idea doesn't mean. It doesn't mean we'll see time reverse someday. The arrow of time in our region is fixed by the entropy gradient we're in. Reversing that would require going back to the conditions of the early universe, something that's incredibly unlikely. These mirror universes are separate branches, each with their own arrow. We don't cross into them. We don't meet their inhabitants. But in the big picture, they complete the symmetry of time. In simple cyclic universes, the universe expands, then contracts, then expands again. Time might be thought of as looping in one direction, but that leads to problems with entropy. In each cycle, entropy would increase, and eventually the universe would reach a point where no more cycles are possible. Or it would lose all structure entirely. Bidirectional models don't have that issue. Since entropy grows in both directions, there's no need to erase it between cycles. Each side is complete on its own. There's no bounce, just two arrows pointing away from a central low entropy moment. There's also work in statistical physics and information theory that supports the idea. In simple systems, if you pick a low entropy moment and let the particles evolve forward and backward, entropy will increase in both directions. That's just the natural way things spread out from order to disorder. Our universe may be following the same rule, just on a much larger scale. If time can point in two directions, then the way we see the world, past behind us, future ahead, might not be universal. It might be local, tied to our place in the entropy curve. Some physicists are trying to explore these ideas through simulations and mathematical models. It's even possible that time is not a river, but a branching structure, a kind of tree where each limb has its own direction. If that's true, then our arrow of time is just one path through a much larger whole. There could be other branches, other arrows, and other kinds of experience, some going forward like ours, others going in the opposite direction, all emerging from a shared root deep in the early universe. If this is how time works, then we may never see the mirror. But we might be part of a cosmic symmetry that stretches far beyond what we can observe, a balance of past and future. Tachyon condensation and universe creation. Among the more unusual ideas in theoretical physics is something called tachyon condensation. To most people, the word tachyon sounds like something from science fiction. It's often linked to particles that move faster than light, which already sounds strange. But in the context of string theory, tachyons are not particles in the ordinary sense. They are mathematical signs that something in the theory is unstable. Where normal particles show up as stable energy states in a quantum field, tachyons suggest that the energy is sitting on top of a hill rather than in a valley. In other words, the system wants to change. And when it does, the process is called tachyon condensation. In string theory, tachyon fields behave like a hilltop. The presence of a tachyon means the current setup is not the lowest energy version of itself. When the tachyon condenses, that is, when the field changes and settles into a lower energy state, it creates a new kind of vacuum. In some models, that vacuum can lead to the birth of a new universe. This idea sits at the intersection of high-energy theory, cosmology, and aspects of quantum gravity. It starts from the observation that many configurations of space and fields are not permanent. They decay or transform. Tachyons, in string theory, often show up in systems that are unstable because they include things like brains. A tachyon field marks the point where the brain begins to dissolve or collapse. But as it collapses, something else may form. New structures can appear in the resulting vacuum. Some of those may be the seeds of entirely new regions of space. This process has mathematical support in certain versions of string theory, especially in what's called bosonic string theory and superstring theories with broken symmetry. In those contexts, tachyons are not placeholders. They appear as solutions to the equations, which describe the energy landscape of possible universes. The condensation smooths out this landscape, and when it does, it may break symmetry, reshape geometry, or even split off parts of space. One model that makes use of this involves bubble nucleation. When a tachyon field condenses, it lowers the energy of the vacuum in one spot. That region then expands, forming a bubble of lower energy space inside a higher energy background. The boundary between the two is like a moving wall. If the bubble grows large enough, it can become its own universe, detached from the original space. Our own universe may have been born from a tachyon condensation in a higher dimensional or more energetic space. That prior space might no longer exist in any detectable form, but its instability left behind our cosmos as a kind of remnant. There's a natural connection here with inflation. Some versions of inflation theory use scalar fields that act a lot like tachyons. They roll down a potential slope and eventually settle into a low-energy state, releasing energy into the universe. In fact, some researchers have tried to model inflation itself as a kind of tachyon condensation. In those versions, the inflaton is actually a tachyon field that brings the system from instability to stability, fueling cosmic expansion along the way. But tachyon condensation goes even further. In string theory, space and time themselves are not always fixed. They emerge from deeper properties of the theory. So when a tachyon condenses, it doesn't just change the energy, it can also reshape geometry. It might pinch off one direction of space, or it might create new dimensions. Some models even suggest that entire branes can appear from the process. In these cases, the word creation doesn't mean something popping out of nothing. It means a shift, a reorganization of the fabric that underlies space and time. One kind of structure decays, and another takes its place. The tachyon is the trigger. The condensation is the transition. The bubble is the result. And the new universe is what grows inside that bubble. After a tachyon condenses, does the new vacuum last forever, or can it decay again? Some models suggest that multiple transitions are possible, each one leaving behind a new vacuum. In that case, universes might chain together, one emerging from the instability of another in a never-ending sequence. Some universes may be the stable endpoints, while others might be temporary bubbles, destined to collapse or to spawn new spaces. While experimental support is not yet close, the mathematical tools used to study tachyon condensation are getting more refined. Researchers are mapping how branes behave, how fields evolve in unstable vacua, and how these changes ripple through space. They're using string field theory and higher dimensional geometries to simulate what might happen. These efforts are not limited to high-energy physics. One of the stranger ideas to come from this is that tachyons might not just lead to new space, they might erase old space. If the original brane decays completely, then the space it held could vanish. This introduces the possibility of cosmic death as well as birth. Tachyon condensation links instability, field dynamics, and vacuum transitions in a way that might describe universe creation. Whether it ever happened to us is still unknown, but it is a rich area of inquiry that is worth further exploration. Was time an emergent property of the early universe? In many quantum theories of gravity, time isn't a basic part of the equations. Instead, it disappears. These models describe the universe as a whole without referring to a flowing time. This gives rise to the idea that time might not be fundamental. It might be something that emerges, like a shadow cast by deeper relationships, or a pattern that appears only when enough pieces fall into place. One way to understand this is through something called entanglement. In quantum mechanics, entanglement refers to a link between particles or systems, where the state of one is tied to the state of another. You can't fully describe one without the other. They are connected, no matter how far apart they are in space. But entanglement doesn't just apply to small things. Some theories suggest that the entire structure of space-time, including space and time, emerges from webs of entanglement between tiny quantum pieces of information. The idea is that when enough quantum systems are entangled in just the right way, space and time as we know them begin to take shape. It's like a 3D image appearing from a pattern of pixels. Researchers like Fotini Markopoulou and Carlo Rovelli have proposed that what we experience as time might not exist on its own. Instead, it might be a side effect of how quantum systems interact and become entangled. The more entanglement there is between systems, the more time seems to exist between them. This leads to a view known as relational time. In this picture, time isn't something absolute, ticking away in the background. It's something that shows up only when things relate to each other. If you have a universe with only one object, there's nothing for it to interact with. But once there are multiple systems, and those systems begin to interact or evolve relative to one another, a kind of time emerges. Some experiments in quantum information science already show how this can work. In certain isolated systems, you can create a situation where the system evolves as if time is flowing, even though the full description of the system doesn't include any time variable at all. The flow of time is reconstructed from how one part of the system changes compared to another. The Wheeler-DeWitt equation is supposed to describe the entire universe in a timeless way. It contains no ticking clock. Instead, it gives a picture of all possible states of the universe, all existing together in a kind of timeless wave function. In some interpretations, time emerges when we focus on certain parts of that wave function. As observers, we see one version of events unfold, a kind of internal clock ticking inside the bigger picture. In this view, time is something we experience because of the way we're embedded within it. This is sometimes called the clock inside the system idea. We see time because we're part of a system that changes. That change is real, but the overall system might not be evolving in any absolute way. It's like being inside a movie. The story moves forward for you, but the film already contains the entire sequence. You experience time, even though the full movie exists all at once. Researchers like Barber take this idea even further. He suggests that the universe is made of timeless nows. These are snapshots, moments of the universe's configuration that don't evolve. But some configurations contain the memory of others. In those snapshots, we feel like time has passed, even though everything actually exists as a kind of frozen structure. Time, in this case, is an illusion generated by memory and structure within certain moments. If the laws of physics don't include time, then how can we talk about causes and effects, about before and after? None of these ideas are settled. We don't yet have a complete theory of quantum gravity. We don't fully understand how space, time, and matter emerge from deeper laws. But more and more physicists are exploring these questions, using tools from information theory, thermodynamics, and quantum field theory. The hunt for pre-Big Bang fossils, CMB anomalies, and what they might mean. The CMB is one of the strongest pieces of evidence we have for the Big Bang. It's like a photograph of the young universe, showing us the moment when matter and radiation separated and light could finally travel freely through space. This ancient light is nearly the same in every direction. It has small fluctuations, tiny temperature differences across the sky, that tell us about the early clumping of matter, which later grew into galaxies and clusters. These fluctuations match what we'd expect if the universe had expanded from a hot, dense state and gone through a period of rapid inflation. But over the last few decades, as scientists have studied the CMB in more detail, they've found some strange features. These features don't line up with the standard predictions, and while no single one is enough to rewrite the theory of the Big Bang, taken together, they raise questions. One of the best-known anomalies is the so-called cold spot. It's a region in the southern hemisphere of the sky that appears slightly cooler than expected. It's a large, extended patch covering an area of several degrees. Some models of inflation allow for this kind of feature to happen by chance, but the cold spot is unusually deep and wide. Researchers have suggested it might be caused by a giant void in space, a vast region with less matter than average, which could make the CMB photons lose energy as they pass through. Others think the void explanation doesn't fully account for the cold spot's depth. What if the cold spot is something else? Some have proposed that it could be a fossil of a past event, an imprint left by something that happened before the Big Bang. In cyclic models or bouncing cosmologies, features from an earlier cycle might carry through into the next one. Another curious anomaly is called the axis of evil. This name, which was originally meant to be light-hearted, refers to a strange alignment in the large-scale temperature patterns of the CMB. If you look at the longest wavelengths in the CMB, the ones that cover the most sky, they don't appear to be randomly distributed. Instead, they seem to line up along a common axis. This is unexpected. The standard model of cosmology assumes the universe is isotropic and homogeneous, meaning it should look the same in every direction on large scales. An alignment like this suggests there might be a preferred direction in space. This kind of alignment could be caused by something local, such as contamination from the Milky Way. But after careful data cleaning by missions like WMAP and Planck, the alignment remains. Some researchers believe it could be a statistical fluke, but others take it more seriously, wondering whether it points to something outside our standard understanding. In some pre-Big Bang scenarios, this kind of alignment could be the result of interactions between our universe and another one before or during the Big Bang. In Penrose's CCC, for example, certain features in the CMB, including alignments and cold regions, might be echoes from the previous eon. Penrose has even claimed to find circular patterns in the CMB that he believes could be the imprints of black hole collisions from an earlier universe. There's also the problem of hemispherical power asymmetry. In simple terms, one half of the sky appears to have slightly more variation in temperature than the other. This shouldn't happen if the universe is truly the same in every direction. The standard inflationary model predicts that the temperature fluctuations should be statistically uniform, but the CMB data shows a small, persistent difference. It's not large enough to break the model on its own, but it adds to the growing list of curious features. One idea to explain this asymmetry is that the inflationary field might have had a small tilt or gradient. If the inflaton field wasn't perfectly smooth, then different regions of space might have inflated slightly differently. That could leave a subtle imprint in the CMB. Some suggest that the asymmetry could be the result of our universe being part of a larger structure, perhaps a multiverse, where different regions have different properties. Some anomalies are even harder to describe. When researchers divide the sky into patches and analyze the statistics of the temperature fluctuations, they sometimes find slight differences in how the fluctuations behave. These include unexpected alignments between different modes of the temperature data and signs of non-Gaussianity, patterns that deviate from the expected bell curve shape. If any of these anomalies turn out to be real and not just data artifacts, they could provide a rare window into physics beyond the Big Bang. Most of our theories about the early universe are limited by what we can observe. The CMB is like a wall. We can't see through it. But if traces of pre-Big Bang activity left a mark on the CMB, then we might be able to learn something about what came before. Researchers have tried to test these ideas with data from multiple missions. The Planck satellite confirmed the existence of many of these anomalies, but it didn't settle the question of their origin. Future missions, especially those that can detect the polarization of the CMB more precisely, might offer new clues. There's hope that other kinds of cosmic signals might help, but the CMB remains our best direct probe of the very early universe. If there are fossils from before the Big Bang, that's where we're most likely to find them. Roadmap for future probes. LISA, planned for launch by the European Space Agency in the 2030s, will look for a quiet, persistent background of gravitational waves. Some models suggest that brane collisions, quantum bounces, or phase transitions in the vacuum before the Big Bang could generate these signals. If detected, they would be almost impossible to explain through post-Big Bang astrophysics alone. Other gravitational wave efforts look in different frequency ranges. The pulsar timing array projects, like Nanograv and the European Pulsar Timing Array, use millisecond pulsars, very stable cosmic clocks, as a kind of galaxy-sized detector. They look for minuscule delays in the arrival times of pulsar signals, caused by low-frequency gravitational waves passing between the pulsar and Earth. Recently, these projects reported a common signal hinting at a background of gravitational waves. While not yet confirmed to be cosmological in origin, some researchers are checking whether such a signal could point toward features imprinted before the observable universe began expanding. Axions are hypothetical particles that might explain the strange behavior of quantum chromodynamics, the theory that describes strong nuclear forces. But they also appear in many models of string theory and early universe physics. If axions exist and are very light, they could have been generated before or during the earliest cosmic events and now fill space like a gentle fog. Experiments like ADMX or the axion dark matter experiment use resonant cavities cooled to near absolute zero, searching for tiny conversions of axions into photons inside a magnetic field. Future axion detectors will try to go deeper, possibly even testing forms of axion behavior predicted in pre-Big Bang contexts. On another front, radio astronomy is providing more clues than ever. The 21-centimeter hydrogen line, emitted by neutral hydrogen atoms, serves as a powerful probe of the early universe. Projects like the Hydrogen Epoch of Reionization Array and the Future Square Kilometer Array aim to map the distribution of hydrogen across billions of years. Some researchers hope to find small irregularities or shadows that don't match known physics. These may turn out to be fossil imprints from events that occurred before cosmic inflation, or even from interactions between bubble universes in a multiverse. High-altitude and space-based particle detectors are also being reimagined. Balloons like Anita have picked up strange particle events that come up from the Earth rather than down from space. Though most are likely explainable through known interactions, some have raised eyebrows. Could these be particles from a universe that intersected ours or left traces during a pre-Big Bang collision? One especially creative idea comes from proposals to use lunar observatories or satellites parked far from Earth. The Moon has no atmosphere and no magnetic field, meaning detectors placed there might pick up cleaner signals from space. Some missions have proposed building radio telescopes on the far side of the Moon to shield them from Earth's interference. Others imagine gravitational wave detectors using long arms laid out on lunar soil. These might one day track ultra-low frequency waves, possibly left behind by very ancient cosmic events. Though none of these tools can give immediate answers, each has a specific target. Each of these experiments, in its own way, chips at the edge of the known. Together, they build a roadmap, not just to test the physics of the Big Bang, but to go back even further. Simulating the unspeakable. What computer models say about pre-Big Bang physics. Computer simulations have become an essential part of modern physics, especially when the problems being studied cannot be tested in a lab or seen through a telescope. Nowhere is this truer than in the study of the universe's earliest moments. The idea of anything before the Big Bang pushes theories and tools to their limits. Without direct observations or experiments, scientists rely on math, logic, and more recently, raw computing power. The digital world becomes a kind of lab, one where space, time, and matter can be rewritten line by line in code, letting us explore what physical laws might look like when pushed to the extremes of energy and scale. One of the main techniques used to explore this frontier is known as lattice quantum gravity. At its core, this approach tries to answer the question of how gravity works when space and time themselves are no longer continuous, but broken down into tiny chunks. Imagine a grid or lattice where each point connects to its neighbors, much like pixels on a screen. In this view, space-time becomes a network. Simulations run on this kind of lattice can test how space might behave at the smallest possible scale, far beyond what general relativity was designed to handle. By feeding in different assumptions and mathematical rules, researchers can see how a small patch of quantum space-time might grow, curve, or even bounce back and forth. Some of these simulations suggest that under certain rules, a classical space-time, the kind we live in, can condense out of a much more chaotic and structureless state. One well-known example is causal dynamical triangulations. Here, space and time are chopped into tiny triangles and stacked in ways that respect the direction of time. Unlike other methods that let time loop or tangle, this approach keeps causality intact. When run on powerful computers, the model can grow large-scale structures that resemble the kind of smooth space described by general relativity. These kinds of results give weight to the idea that a full space-time could emerge from something far simpler or stranger, perhaps even from nothing at all. Another approach that draws interest is based on holography, The holographic principle suggests that the information describing a volume of space can actually be stored on its boundary. This means the universe, or parts of it, could behave like a three-dimensional projection of a two-dimensional set of instructions. In practical terms, this allows simulations that don't need to model every detail of 3D space. Instead, researchers can run models that live on a 2D surface and yet reflect how the full 3D system should behave. The most famous example of this comes from string theory, where a model called anti-de Sitter conformal field theory, or AD-CFT, creates a bridge between gravity in a volume of space and quantum physics on its surface. Though our universe doesn't match the exact shape required for that model, variations are being tested. These simulations might tell us how a universe can arise from a boundary-like shell, and whether such boundaries could form naturally in a pre-Big Bang phase. Yet another use of simulation is in tracking false vacuum decay. Many cosmological theories rely on the universe being trapped in a false vacuum. But because quantum tunneling is a random and rare event, it's difficult to study through equations alone. Simulations are run to estimate decay rates, bubble formations, and how the new vacuum might spread across space. In some models, this kind of tunneling could even happen between different pocket universes. There are also hybrid models, combining different simulation types to see how variables interact. For instance, a lattice-based geometry could be combined with a false vacuum decay simulation to see how geometry itself reacts to changes in vacuum energy. Do bubbles form only under certain conditions? Do they collapse, expand, or cause space to ripple outward? These are questions that cannot yet be answered through observation, but simulations provide a testbed. By adjusting parameters, like the number of dimensions, the energy scales involved, or the coupling strengths between forces, scientists can see which conditions lead to stable or unstable universes. These digital tools are also being used to reverse engineer the observed universe. Some researchers take patterns seen in the CMB or large-scale structure and work backward, simulating what kinds of pre-Big Bang physics might lead to those outcomes. While this doesn't give direct evidence of any specific theory, it helps narrow the list of possible models. If a theory cannot produce the universe we see today under any reasonable conditions, it can often be set aside. In this way, simulations act as a filter, allowing only the most plausible ideas to pass through to further study. One of the most ambitious efforts in this area involves using quantum computers. Still in their early days, these machines handle data in a way that mimics quantum systems more directly than classical computers can. In the future, they may be able to simulate entire pre-Big Bang environments with a level of detail that's now impossible. Already, early tests are being run on small quantum systems to explore ideas like vacuum transitions, entanglement entropy, and quantum cosmological wave functions. However, computer simulations have limits. They require assumptions about initial conditions, laws of physics, computational steps that may not hold in the actual early universe. There's also the question of how to interpret results. If a simulation produces a stable spacetime, does that mean the model is right? Or could it be a lucky outcome among billions of failed runs? Without experimental data to guide them, simulations can easily become a kind of digital exploration of possibilities rather than firm predictions. Still, even as they live in the world of what-ifs, they allow progress where traditional math and telescopes reach their edge. Many of the theories touched on in earlier sections now rely on simulations as part of their development. Each simulation adds a bit more texture to the picture. Some show how geometry alone might give rise to time. Others test how a chaotic quantum sea could settle into order. A few even allow for entirely new physical laws governing worlds that may never exist, but help us define the boundaries of the one that does. As computing power grows and algorithms improve, the simulations will only become more realistic and varied. In time, they may do more than speculate. They may offer something close to understanding. And in the face of a mystery as vast as what came before the universe, even a digital echo of what might have been is something to hold on to. Neutrinos. From nowhere, could particle relics be older than the universe? Neutrinos are among the most mysterious particles known in physics. They are incredibly light, barely interact with matter, and travel at nearly the speed of light. For decades, physicists saw them as silent bystanders to the more noticeable actors of the Standard Model. But over time, they have come to represent something more, possible messengers from the deepest past, carrying information not just from the early moments of our known universe, but perhaps from epochs that existed before the Big Bang. The known types of neutrinos, electron, muon, and tau, are all accounted for in current experiments. These active neutrinos are produced in processes like nuclear reactions in the Sun, radioactive decay on Earth, and cosmic ray collisions in the atmosphere. They were also created in large numbers during the early hot stages of the Big Bang. As the universe cooled, a cosmic neutrino background formed, similar to the better-known CMB, but with far weaker interactions. This neutrino background, frozen since the first seconds of the universe, is thought to still be drifting through space today. Unlike photons in the CMB, these relic neutrinos are almost impossible to detect directly. They have extremely low energy and don't interact with regular matter in a way that makes them easy to observe. But they are predicted by standard cosmology, and their presence affects the evolution of the universe in subtle ways. For instance, they slightly alter the pattern of cosmic structure formation and leave an imprint on the CMB itself. That much is generally accepted. But in recent years, researchers have begun asking more daring questions. What if not all neutrinos come from the Big Bang? What if some of them, or certain versions of them, predate it? One version of this idea involves sterile neutrinos. These are hypothetical particles that do not interact through any of the known forces except gravity. They don't appear in the Standard Model, but they are a natural extension of it in many theories. If sterile neutrinos exist, they could have been produced in a time before the known universe began expanding. They wouldn't have to follow the thermal history of the universe we know. Instead, they could have formed in a colder or more exotic phase of space-time, perhaps during a bounce from a previous universe, or in a decaying vacuum that later inflated into ours. In some models, the universe was once static or slowly evolving. In others, the universe goes through cycles. If any of these are correct, then particles like sterile neutrinos could have originated in that earlier phase. Unlike photons or charged particles, neutrinos can travel through incredibly dense and chaotic environments without being absorbed. This means that they can pass through periods of high temperature or energy without losing their identity. If certain types of neutrinos formed before our universe heated up, they might still be around, unchanged. And because they interact so little with other particles, they could move through space almost untouched, still carrying information about the state of the cosmos before it became what we know. Some experiments have hinted that sterile neutrinos might exist. These hints are still controversial. For example, a few short baseline neutrino experiments, where neutrinos are fired across a relatively short distance and then counted, have shown slight mismatches between expected and actual results. These mismatches could be explained if a small fraction of the neutrinos changed into an unknown type during the flight. But other experiments have not confirmed this, and the data remain unclear. Still, the search for sterile neutrinos continues, not only in Earth-based detectors, but also in cosmological data. If a background of exotic neutrinos exists, it could show up in the behavior of the early universe. It could affect the total number of light particles inferred from the CMB, or change the rate at which the universe expanded in its first few minutes. Scientists use measurements from the CMB and primordial element abundances to place limits on how many light particles were present. So far, these results put strong constraints on any extra particles, but they don't rule them out completely. Another line of research looks at very high-energy neutrinos from cosmic sources. Observatories like IceCube, buried deep in Antarctic ice, detect rare interactions from neutrinos coming from space. Most of these are believed to come from energetic cosmic events like supernovae or colliding galaxies, but a few of them appear to be extremely energetic and don't match any known source. If some of these neutrinos don't fit the profile of astrophysical production, they could point to processes from the very early universe, or even from a phase before it began. During a false vacuum decay, various quantum processes would have occurred, including the spontaneous appearance of particles. If neutrinos were among these particles, they might have been produced in a way that isn't tied to the later thermal history of the universe. If that happened, we might detect signs like small deviations in the energy distribution of the cosmic neutrino background, or unexpected patterns in how neutrinos oscillate between types. The patterns might not match those expected from a uniform thermal bath left over from the Big Bang. They could show evidence of a more exotic origin. In this sense, neutrinos could serve as direct messengers from beyond the visible limits of space and time. They could be older than our observable universe, shaped by unknown physics. Their presence wouldn't prove what came before the Big Bang, but it would strongly suggest that something did. There is speculation that some anomalies in current neutrino data might hint at such pre-Big Bang origins. Certain unexplained features in reactor experiments could just be due to experimental error or unknown systematics, but they could also point toward unknown forms of neutrino behavior. And if sterile or pre-thermal neutrinos are part of the answer, it could mean that our universe is only the latest stage in a longer story. In the years ahead, new detectors and missions are aiming to offer better sensitivity to both terrestrial and cosmic neutrino signals. Projects like Ptolemy aim to directly detect the cosmic neutrino background, a task once thought impossible. If successful, they could measure the properties of these relic neutrinos with enough detail to detect deviations from standard predictions. Any hint of extra types, unusual energy distributions, or unexplained patterns would open the door to questions that reach far beyond the Big Bang. Whether such neutrinos are truly from nowhere, or from a place we just don't yet understand, remains uncertain. But their ghostly presence across space and time may hold answers to some of the deepest mysteries in cosmology. Can black holes leak clues about other universes? Holography and pre-bang information. Black holes have long been thought of as the ultimate endpoint of matter and energy, but over the last several decades, views on them have shifted dramatically. Instead of only swallowing matter, black holes may also store information. One of the biggest changes in thinking came when researchers discovered that black holes aren't entirely black. In the 1970s, Stephen Hawking showed that black holes emit a tiny amount of radiation, now called Hawking radiation. This meant that black holes have a temperature and entropy, much like ordinary systems. Over very long timescales, a black hole can evaporate, shrinking as it emits radiation. But this creates a serious problem. Where does the information go? In classical physics, when something falls into a black hole, it's lost forever. But in quantum physics, information cannot be destroyed. The puzzle, known as the black hole information paradox, has become one of the central issues in theoretical physics. How can a black hole disappear, yet preserve the full details of everything it swallowed? If the information is truly lost, then one of the most basic rules of quantum theory is violated. Some researchers have tried to solve the paradox by suggesting that information is not lost, but encoded in the black hole's surface, which would be its event horizon. This is where the holographic principle enters the picture, which itself gained wider attention with the development of the ADS-CFT correspondence. This mathematical duality connects a type of gravity in a space with negative curvature, anti-de Sitter space, to a quantum field theory on the boundary of that space. What happens in the bulk volume of space, including black holes, can be exactly described by a theory without gravity on the boundary. Though our universe is not anti-de Sitter space, the correspondence provides a powerful tool. It shows that gravity and quantum theory might not be separate. Instead, they could be different views of the same thing. And if this holds more generally, black holes could become windows into a deeper structure of reality, where space, time, and the Big Bang are emergent phenomena. Some physicists believe that by studying how black holes store and release information, we might be able to learn about regions beyond our observable universe. These might include earlier phases of cosmic history or other universes. The reasoning is that if a black hole somehow interacts with structures or fields outside our familiar spacetime, those interactions could affect how it encodes information. This brings us to a controversial proposal involving firewalls. In 2012, a group of physicists suggested that if black holes preserve information, then their event horizons might not be smooth as predicted by general relativity. Instead, they could be regions of intense energy, a firewall that destroys anything falling in. The idea was proposed as a way to preserve the rules of quantum theory while resolving the paradox. But it creates a clash with the equivalence principle of relativity, which says that falling into a black hole should be uneventful at first. The debate over firewalls is ongoing, but it underscores how complicated the questions about black holes have become. Some versions of the firewall idea suggest that the information stored in a black hole is not just from its own formation, but could be entangled with information from far outside our universe. If spacetime is part of a larger system, then the black hole's content might reflect that broader reality. There are also suggestions that the inside of a black hole could be linked to regions that are not part of our universe. In some theoretical models, black holes are connected by structures called wormholes or Einstein-Rosen bridges. These could act as tunnels to other regions of space or even to other universes. Normally, these wormholes collapse too quickly to be used, but in the context of holography and entanglement, they may behave differently. One example is the ER equals EPR conjecture, which proposes that entangled particles are connected by microscopic wormholes. This would mean that quantum connections across space have a geometric counterpart. Imagine a black hole in our universe that formed from the collapse of a star. According to traditional views, this process is local. It reflects the history of that particular star and nothing else. But if black holes are tied into a broader web of spacetime or entanglement that includes regions beyond our own, the process of black hole formation might involve more than just local events. It could bring in information from a shared quantum state, one that reaches back to before the Big Bang, or sideways into other universes. Some researchers are using tools from holography and quantum information theory to study how entanglement patterns change over time. One finding is that the interior of a black hole, what we usually think of as a hidden one-way region, can sometimes be described in terms of operations performed on its radiation. This suggests that the inside might not even be a separate place, but a kind of mirror of the outside world. If that's true, the information inside a black hole might be accessible in principle, just encoded in an unfamiliar way. This shifts the question, where instead of asking whether black holes are windows into other universes, we might ask whether our own universe's structure is already linked, through entanglement and holography, to a broader system. Black holes, as extreme objects where quantum gravity becomes visible, could simply be places where this connection is easier to see. Some cosmologists have proposed that the Big Bang itself might have been a kind of horizon, not unlike a black hole's event horizon. In this view, the apparent beginning of time could be a surface beyond which we can't see, but which still holds information. If the Big Bang has a holographic description, then perhaps its interior, what came before, is encoded in subtle ways in the physics we observe today. Black holes, by showing us how holography works in strong gravity, might offer a model for how to decode that information. To explore this, researchers are building models that combine the tools of black hole physics with those of cosmology. They study how entropy changes in expanding universes, how entanglement spreads through curved spacetime, and how different choices of vacuum states affect what we see. Some simulations show that certain features of the early universe can be reproduced by processes that resemble black hole evaporation. This could mean that aspects of our observable cosmos are shaped by dynamics that tie back to an earlier or broader reality. It's also possible that tiny black holes, perhaps formed in the early universe, could still exist today. These so-called primordial black holes might be detectable through their evaporation or gravitational effects. If they exist, and if they follow the same holographic rules, they could be a kind of probe into the physics of the pre-Big Bang era. Each one would carry a piece of the early cosmic puzzle, stored in a way that doesn't require light or traditional matter. Black holes are already hard to study directly, and the information they might contain is subtle and difficult to extract. But the fact that different parts of physics, gravity, quantum theory, information theory, and cosmology are all converging around these objects suggests that they are more than just cosmic curiosities. Why cyclic models are so tempting, and why they often fail. The basic picture of a cyclic universe has been around for a long time. In ancient times, many cultures imagined time as a wheel or circle. In modern science, the idea came back in the early 20th century, when general relativity showed that the universe could be curved and dynamic. Some early versions imagined a universe that expanded for a while, then slowed, then reversed and collapsed in a big crunch, only to bounce and begin again. Each cycle would start with a new phase of expansion, replacing the end of the previous one. In recent decades, new ideas have refreshed the picture. Some models build on string theory or higher dimensional brane cosmology. Others use scalar fields to drive the cycles. These newer versions don't necessarily need the universe to crunch all the way to a point. Instead, they allow for a smooth bounce, avoiding the singularity that classical gravity would otherwise predict. This gives them a modern quantum flavor. It also helps them sidestep one of the oldest criticisms, that a contracting universe always leads to a singularity where physics breaks down. These models have a lot going for them. They give the universe a longer history. They offer a way to explain some of the observed features of our cosmos without relying on a rapid burst of inflation. And they avoid the strange metaphysical baggage of a singular beginning, with time and space emerging from nothing. Instead, they give the universe a rhythm, a regular heartbeat that has always been there. But this beauty comes with deep problems. One of the biggest is entropy. If each cycle of the universe ends with more entropy than the one before, then over time the cycle should get longer and more spread out. Eventually, the universe would become too disordered to bounce back. Galaxies would be torn apart, stars scattered, and everything reduced to radiation and cold particles. Some proposals try to solve this by having the expansion phase stretch out the universe so much that the leftover entropy becomes diluted, spread so thin that it no longer matters. Others suggest that entropy might somehow leak into extra dimensions, leaving our brane clean for the next cycle. But there's no known mechanism that reliably removes entropy in the right way without creating new problems. In many cyclic models, small changes in one cycle can grow and throw off the next. A tiny deviation in the bounce, a little extra energy in the scalar field, or a slight irregularity in geometry can lead to a runaway effect. After enough cycles, the universe might no longer bounce. It might crunch permanently or expand forever. This means the models require careful fine-tuning. That kind of balance doesn't sit well with the goal of a natural, self-regulating cosmos. Then there's the singularity issue. Even in newer models, where the bounce avoids a full collapse, the moment of turnaround, where contraction ends and expansion begins, can still be problematic. General relativity doesn't like bounces. Under ordinary conditions, it predicts that a collapsing universe leads to infinite density and temperature. To avoid this, cyclic models rely on quantum effects, exotic matter, or modifications to gravity. None of the current models have shown a fully consistent bounce mechanism that works in every situation. Cyclic models also face tension with observational data. The standard inflationary model makes clear predictions about the pattern of fluctuations in the CMB. Cyclic models can mimic some of these effects, but so far, no cyclic model has matched the precision and consistency of inflation. Some versions predict small differences in the power spectrum or non-Gaussian features in the CMB, but these are hard to detect and often fall within current error margins. On top of all this, there's the question of testability. A truly cyclic model should leave some trace, but most models don't clearly predict such signals, or they rely on effects that are too faint to observe. If every cycle erases the memory of the one before it, then the model becomes difficult to confirm or falsify. Newer proposals keep trying to refine the bounce, improve entropy handling, and link the theory to observations. Some researchers explore models where only a few cycles have occurred, rather than an infinite series. Others consider asymmetric cycles, where each bounce leads to slightly different physics. It's not hard to see why scientists keep returning to the cyclic idea, but making it work in detail remains a steep hill to climb. The math is delicate, the assumptions heavy, and the evidence thin. Every attempt at a cycle seems to wrestle with the same fundamental forces: entropy, instability, and the difficulty of bouncing back from collapse. Could consciousness be older than our universe? When quantum mechanics emerged in the early 20th century, it changed everything. It revealed that the act of measurement was not a passive process. Observing a system wasn't just watching it, it changed it. Before a measurement, particles didn't seem to have definite properties. Only after observation did they choose a position, or a momentum, or a spin. This has led to long debates about what the observer's role actually is. Is the observer just another part of the system? Or is there something special about observation, something tied to awareness? Some interpretations of quantum theory, like the consciousness causes collapse idea, suggest that the wave function only becomes real, only collapses, when observed by a conscious mind. Most physicists reject this view, but it hasn't gone away. It keeps coming back, especially when people try to understand the deepest foundations of quantum mechanics. What is an observation really? And what is an observer? In quantum mechanics, systems evolve based on probabilities until they're measured. But what about the entire universe? There's no external observer to measure it. So, what collapses the universal wave function, if anything? Some researchers wonder if consciousness, or proto-consciousness, could play a role not just in small quantum events, but in shaping reality itself. This brings in ideas from a different field altogether, philosophy of mind. For centuries, thinkers have debated whether consciousness is something that can be fully explained by physical systems. Is it just a byproduct of complex brains? Or is it something more basic, something that doesn't depend on biology or matter at all? Some philosophers, especially those exploring panpsychism, suggest that some form of consciousness, or proto-consciousness, might be a fundamental part of the universe, not a product of it. If that were true, then it raises a wild possibility. Maybe consciousness doesn't come after the universe. Maybe it came before. Maybe it's not even in the universe. Maybe consciousness, or something like it, is part of the same root-level stuff that gave rise to space, time, energy, and all the rest. It might be as basic as mass or charge, or even more basic than that. In some interpretations of quantum theory, information plays a more fundamental role than matter. The wave function, after all, is not a thing. It's a description, a mathematical object that tells us what we can know about a system. And the limits of what we can know, the uncertainty principle, for example, suggest that information and reality are deeply linked. The famous physicist John Wheeler once proposed the idea of it from bit, meaning that the physical world arises from bits of information, rather than the other way around. And information, unlike energy or matter, doesn't have to exist in space. It's an abstract quantity. Some have asked whether this information, the basic difference between up and down, between existence and non-existence, might not just precede the universe in time, but stand outside time entirely. Could there be an informational field, or a field of pure possibility, from which the universe emerged? At this point, the boundary between physics and metaphysics becomes very thin. Some theories in physics now deal with systems that don't have time as a variable. They talk about timeless equations. In such a world, perhaps consciousness must also be timeless, not something that arises when matter gets organized a certain way, but something woven into the structure itself. Could the act of observation or experience be baked into the structure of reality itself? Some researchers exploring integrated information theory, or IIT, in neuroscience argue that consciousness is not something produced by a brain, but something that corresponds to a very particular kind of organized information. In theory, any system with the right internal connections and relationships could have some degree of awareness, not like human awareness, but a faint glimmer of experience. If that's true, then consciousness might be less like a flame that turns on when matter gets complex, and more like a pattern that's always present in the universe, just in different intensities. From this point of view, the early universe, or even the pre-universe, might still carry the seed of consciousness. It might be built on rules or structures that make experience possible. And if those structures are more basic than space or time, then they may have existed before the Big Bang or outside it. Some thinkers go even further and suggest that consciousness might not just be one of many ingredients, it might be the only one. This is the territory of idealism, the view that mind is the fundamental substance and matter emerges from it. It's a minority view in science, but it has a long tradition in philosophy. And when science runs into hard walls, like the beginning of time or the mystery of measurement, it sometimes loops back to these old ideas and sees them in a new light. Of course, there's no experiment that can prove that consciousness is older than the universe. These are not the kinds of questions that can be settled with a particle collider or a telescope. But they keep being asked, because the edges of science are strange places. At those edges, questions about existence, origin, and meaning blur into each other. The standard tools of measurement and logic become harder to apply. And yet, people still try. It's a strange, speculative idea. But in the search for ultimate origins, nothing can be ruled out too quickly. Were there civilizations before our universe? Survival in eternal recurrence. If there were other cycles before this one, could life, intelligence, and even civilization have existed in those older versions of reality? And if so, is there any way we might find signs of them today? If the universe does repeat or cycle, the question of memory becomes unavoidable. Can anything survive the passage from one universe to another? Most matter and structure would likely be destroyed in a bounce or reset. But what about information? Could patterns or codes survive in some form, even if they're scattered, distorted, or buried deep in the fabric of space-time? This brings us to the idea of informational fossils. These would not be bones or buildings. They would not be telescopic images or radio signals. They would be deeper and stranger, structures hidden in the laws of physics, in the distribution of energy, or even in the logic of mathematics itself. In a way, they would be evidence not of what was built, but of what was understood. If a civilization became advanced enough, it might understand that its universe was doomed to collapse or repeat. It might then try to pass on knowledge, not through machines or DNA, but through encoding information in the most stable parts of physics, perhaps in the ratios of particle masses, or the curvature of space, or the constants that guide how everything works. This would require unimaginable intelligence and foresight. But if civilizations were not bound by short lifespans or limited resources, they might gradually learn how to shape the next universe from within this one. Right now, humans think about changing their local environment, building machines, altering genetics, exploring space. But an ancient civilization in a repeating cosmos might think bigger. They might study how black holes collapse, how entropy spreads, how space-time curves, and ask whether they could steer the universe itself, just a little, to make sure certain patterns survive the bounce. Some have argued that a black hole may act like a hard drive, storing everything that fell into it in a scrambled but recoverable way. If that's true, perhaps black holes could serve as memory banks, bridges that carry information from one universe to the next, especially if they somehow survive or influence the bounce. It's also possible that certain patterns or codes could become embedded in the initial conditions of the next universe. If the laws of physics are shaped by prior cycles, then maybe there are fingerprints of past intelligence etched into the constants and equations we observe today. It would not be easy to detect such things. We would have to know what to look for and how to separate coincidence from design. But if the same patterns show up across cycles, if they are too precise or too meaningful to be random, they might be hints that something intentional took place long before our own time. If civilizations can exist in the various bubble universes, and if they learn how to travel or communicate across them, however unlikely that seems, then they may also try to pass on knowledge from one bubble to another. This wouldn't be through space travel in the usual sense, but through deeper forms of transmission, perhaps involving quantum entanglement, vacuum fluctuations, or manipulation of the inflating space itself. Even if travel or direct communication is impossible, a very old and advanced civilization might still try to leave behind something like a message in a bottle, a pattern or pulse that might echo across bubbles or cycles. It could be encoded in gravitational waves or in rare features of the CMB. People have proposed that we search for such anomalies, areas where the sky looks too perfect or too ordered to be natural. If another intelligence designed something to survive across universes, would we even know what it looked like? Would we understand it as a message, or just see it as a feature of the cosmos, like any other? The farther back we look, and the more abstract the signal, the harder it becomes to draw a line between nature and intention. That's part of what makes this idea so strange and so compelling. And on that wild note, our journey comes to an end. What other topic would you like to hear about? Comment down below. And if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.